Hello and welcome YouTube, Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Step on aside as we jump into section 7.3 in the Big Ideas Math Integrated Math 3 textbook, where we analyze geometric sequences and series. We just came off of arithmetic sequences in series, and it actually surprised me how many arithmetic sequence things there were, given how much we would have done with it in IM1, or how much we did with it in section 7.1. So I'm probably going to feel the same way. Well, I'm going to be less surprised this time, but you're probably going to expect to see the same kind of thing for the geometric sequence and series set. Now, this is going to be for finite geometric series, at least, because infinite comes in the next section, so we'll see what they talk about then, and that's actually after the quiz portion. So we'll stick with finite series sum formula, and that'll come probably in the later set of 66 problems total. If you want to jump to the description section down below, you can find this PDF for this particular section, as well as the timestamps for every problem up to number 66, and any graph paper that's needed as well. Without further ado, I'm going to start with the lecture portion. Let's go ahead and get started. We're going to identify geometric sequences, and like I said, we kind of did a little bit in 7.1, we did a little bit in IM1, if you want to go back to your IM1 roots, but if you want to go back to 7.1, you can see more when we talk about it. And same with the rules. We'll see their formula that they write. I'm going to have the same thing. Now, geometric sequences are like exponential functions, so unlike the linear stuff I spoke about before in arithmetic sequences, finding different ways to do it, I'm probably going to follow a lot with what the book does. That's probably how I do it a lot as well. Keep that in mind. And find sums of finite geometric series. And we did that for arithmetic series. It was always finite because otherwise it would always go to positive or negative infinity. Not true for geometric. You can have certain ones converge at values even if infinite. Save that for the next section though when we hit finite ones. We're all about the common ratio for geometric sequences and series. Let's go ahead and see what they want to say with it. Yeah, the ratio of any term to the previous term is constant. That means you're multiplying by the same amount each time. You really want to call it multiplication, not division, even if it means multiplying by a fraction. So tell whether each sequence is geometric or not. You have to see if you're multiplying by the same amount. It's not about difference anymore. 6 times what is 12 is 12 times that same number, 20, etc. Well, without doing what they're going to show, which is a great thing that they show, by the way, I'm going to do it in kind of a more conventional way of saying, hey, 6 times 2 is 12, and even if you don't know what you multiply by 12 to get 20, what you multiply with 12 to get 20, we know it's not 2. So we know it's not a common ratio there, and you don't double 20 to get 30 or double 30 to get 42. So we know there's not a common ratio there. Now they happen to find those other ratios by dividing a number by the one before it. That's what you always do. 12 divided by 6 is 2. 20 divided by 12 reduces to 5/3, and these are the reduced fractions of the other ones. Not a common ratio, not a geometric sequence on A. On B, you do get a geometric sequence. You can possibly see, at least from the smaller numbers, that you're dividing by 4, and you can confirm these also divide by 4, but you don't actually call it dividing by 4. Like I said, you state what you multiply by. If you ever want to find out what you're multiplying by, well, dividing by 4th is the same as multiplying by 1/4. You might know that. But divide a number by the one before it. 64 over 256, 16 over 64, etc. All these reduce to that 1/4, which is literally 1 divided by 4, but all of them reduce to that 1/4. The ratio is 1/4. It is common. It is a geometric sequence. Let's look at some of the rules that they have, or at least the rule that they're going to be writing out. You know, in the arithmetic sequence set, we would have one that looks like a sub n equals a sub 1 plus d times n minus 1. And yes, I write the d first there. And I'm not going to explain why the rule is what it is, but this is the rule. But bottom line, you could distribute the d into these two terms. On this one, they have a very similar setup. They have the first term, common ratio instead, and then they have an n minus 1 here instead of common difference. And a common ratio is raised to the n minus 1 power because it describes how many times you multiply by r rather than how many times you add d. That being said, we can't really distribute that r into those two terms, these portions of the exponent. You can sort of, but you generally won't want to. So while we tend to simplify this rule out, you're not often going to see this one simplified. Sometimes you are, and I'll call attention to what it is. If you do want to have a version of that formula, it would be a sub n equals a sub 0 times r to the nth power. Again, this is only if that 0th term makes more sense to use than the first term, and oftentimes for geometric sequences it doesn't, only because it tends to be a fraction or a decimal. So we'll see. The nth term of a geometric sequence of the first term of 2, a sub 1, and a common ratio of 3, boom, is written like that. And by the way, you often want to write the common ratio in parentheses. You have to write it in parentheses if it's a fraction or if it's a negative number. If it's an integer, if it's a positive number, not necessarily, but you're going to see me do it pretty much all the time. Unless there's no term written in front. Okay. Writing a rule for the nth term, write a rule, then find a sub 8. For the rule, you need two things. First term and common ratio. We have a first term here of 5. Common ratio, I'm not going to be cute about it, it's 3. You're multiplying by 3 each time. So with the first term of 5 and common ratio of 3, it would be a sub n equals 5 times 3 to the n minus 1 power. Note, they're even saying the same thing. It is to the n minus 1 power, not n. That's because you are starting from the first term. Same way we do it with common differences. Next one on B, your first term is 88. And your common ratio, if we're dividing by not just 2, but negative 2 as the signs change, that also means you're multiplying by negative 1/2. You do have to state what you're multiplying by. That's how your common ratios appear. And you can tell this negative 1/2 is what's fitting into the parentheses there. And yes, it must be in parentheses when it's a negative so that some signs can turn positive when they're supposed to. And that is your rule. Now, I found the rules for both of them. Let's go for the 8th term, which is what's asked of you. The 8th term, a sub 8 is the 8th term. You substitute 8 for n. So in this one, 5 times 3 to the 8 minus 1 power is 5 times 3 to the 7th power. I would caution you in using your calculator and let it say 8 minus 1 because you might accidentally just raise it to the 8th power and then subtract 1 from the entire result, which is a way different number. We want to raise it to the 7th power. It's a lot faster for you to just do that, in your head and make that happen. Same thing with this one. Raising negative 1/2 to the 7 power times 88, and then you'll get this number here. Now, one thing I want to state for this one here is whether your answer should have been positive or negative based on the negative common ratio, because what it's going to do is change signs each time. The 8th term is an even numbered term. Based on your sequence, the odd terms are positive and the even terms are negative. So I expected my 8th term to give me a negative answer. That's just a little thing you should probably look into to make sure your order of operations are going as expected. Okay, writing a rule given a term and common ratio. This time we'll have some rando term, and we did the same thing for arithmetic sequences, but I went a little overboard with saying here's a different way to do it. Let's just use this form here. And what you need to do is basically find the first term. Now, I can, again, be cute about it, and I can talk about different ways we can get here. But if the 4th term is 12, then we can substitute a sub 4 in for a sub n and 4 in for n. 4 minus 1 is 3, common ratio of 2. 2 cubed is 8. Divide both sides by 8, and you get a value of 1.5 or 3/2. And then, therefore, you can write the rule that way. Because your whole thing to write the rule is to find the first term and common ratio. If they give you the common ratio, you can use it to find the first term with another point. Now, something else I could have done, again, just to make sense of this, is the 4th term is 12 and common ratio is 2. So how do we find that first term with this? We can divide by 2. This time I will say divide because we're just going backwards. You can divide by 2 this way until you get to the first term. Literally, that's what we did for this set because we divided by 8. We divided by 3 powers of 2. 1, 2, 3. And that's how we got there. That explains away the equation. So there's a practical approach. I might look to do that every so often, but the equation is also just fine. They also say plot points. I'm not generally a fan of this with graphs just because I have to change the scale and some of these points get very, very small. So we'll see what they look like. But they say write the first 6 terms. So you do have, I just wrote a few terms out, right? If you know your first term is whatever, multiply by your common ratio each time. If you don't want to substitute values in for n, just say times 2, times 2, times 2. And you can get these points here. And that's probably what I plan on doing, using recursion to build up my 6 points. What's nice about the geometric sequences, a problem's going to be with a lot of fractions. But what's nice about some of the geometric sequence things is they're often not going to give you like a sub 20 because that'll either be a super massive or super small number. So they tend to stay probably as big as 12 at most. Whereas when you saw on the arithmetic ones, we went up to like the 31st term and stuff like that. That's just my guess anyway. I haven't seen it for these problems, but that's what I expect. What if you're given 2 terms? Now, this was something, again, in the arithmetic sequences. I said, hey, this is like y equals mx plus b, slope-intercept form. You know what this stuff's like? This stuff is like that system of equations. I forget the section. I'm thinking about it right now. There was a section in which we wrote exponential function equations given 2 points. I can't for the life of me tell you which one it is. I cannot remember. But we did solve either using substitution or elimination methods based off setting some things up with 2 different equations. So we do have the value of the second term being 12, the value of the fifth term being negative 768, and you can set this thing up by substituting those into those equations. 2 for n, 5 for n in those 2 separate equations. They go with the substitution approach. I think they did that often, and I did a lot of elimination with you as well, so I'll probably swap back and forth, flip-flop. So they divide both sides by r to get a sub 1 written by itself here, and then they substitute 12 over r into a sub 1 into this equation. You can see it's written right there. I'm not going to get deep into how this algebra is done, but they're using algebra to solve for r after that, because this is something that we did solving exponential equations back when. Bottom line, you got to do the work, divide by 12, take the cube root of both sides, and you have a common ratio value. Use the common ratio value into one of your equations, preferably this nice smaller one, to solve for a sub 1, your first term, and you get negative 3. You can, of course, also, actually, I would substitute it into here, which is the same work. You get negative 3. And remember, you're trying to write the rule. Your goal is to come up with the first term and the common ratio. And is there more than one way to do this? Yes. Given that this is the second and fifth terms, once again, here's your first term, unknown, second, third, fourth, fifth. Your second term is 12. Your fifth term is negative 768. And I'm multiplying by some common ratio 3 times to get from one to the other. That means our equation can say 12r cubed equals negative 768. Where have I seen that before? Right here. So, this is where it comes from when you solve for r and we get negative 4. Well, guess what? I can divide here by negative 4 from this term to then get my first term of negative 3. So guys, there are a lot of ways to do it. It's not like you're stuck to using formulas and systems of equations to solve if you don't know how to do that. That's why I bring these things up to say how they tie in, what it is you're doing, and what are some fallback plans. I generally would probably just use this method here, but with the numbers and the points so close, this wasn't all that bad, right? This wasn't all that bad. Okay. Finding sums of finite geometric series. This is the new stuff to you. Now, I'm not going to get too deep into the formula other than show you that this looks a heck of a lot like what we did for arithmetic stuff, only this has a different setup formula. I used to build this proof a lot, so I'd have to look at this hard and see what's going on here. It's kind of creating things for yourself to make it as it is, but they are adding, remember S sub n is the sum, is the series sum, whether it's arithmetic or geometric, it's the series sum. And what you do is you add all of your terms up into your final term here. And hold on, is it the final term? This is the second to last term. And the multiply by negative r. Honestly, I can't remember how this works. I didn't multiply by r. Negative r, I multiply by r. And you'd subtract the results. I can't get into the deep of the why of the matter. I'd have to write out the build. I should have prepped it beforehand and told you what's going on. But you can come up with the equation which cancels out all the middle terms when you add the results of these two things. And what's going on is you're basically finding a way to rewrite this sum based off of canceling out things in the middle that would always be the same, whereas you have two unique terms in a sub 1 and negative a sub 1 times r to the n power, and a sub 1 is a common factor in both terms. When you factor out s sub n from both terms here, you have a 1 minus r inside there, and when you divide both sides by 1 minus r, you get this formula here. Now, I write it pretty much the exact same way. I do. I just have the a sub 1 written on top as a whole. I don't know why. So if you see me write it like this, like that, apologies. This is fine. There's no problem with either one of these. I can see one reason why I might write it the way that I do when we talk about infinite geometric series formula. But either way, guys, what we have is the same thing. This one's a little harder to come across when there's logic involved and such. You have to build the proof off of it. But the nice thing is, if there's one that you have to remember, I guess just take this one. All the other ones you can learn and use in other practical ways, including the infinite series formula, geometric series formula. So there's this one. You need the first term, common ratio, and number of terms. And notice number of terms is just with that numerator, r to the n power. All right, find the sum of a geometric series. Now, first of all, you have to establish that you have a geometric set involved, and we do because your variable is in the exponent of the sigma notation. We're going to find the sum of the first 10 terms here, but using the formula involved. What's also important about this is given this rule, remember, we're not about finding the first term and the last term. like the arithmetic series rule. This one is the first term and the common ratio in the number of terms. So given this formula, our common ratio is 3. You need to note what that formula appearance looks like to pull out the information that we need. This is your first term, given it's to the k minus 1 power, and this is your common ratio here. First term 4, common ratio 3, number of terms 10. So that's n. So the sum of the first 10 terms, substitute 4 for your first term, 3 for your common ratio, and 10 for your number of terms. This one you're going to leave a lot to the calculator to do. There are times where I might simplify some parts. For example, 1 minus 3 is negative 2. 4 over negative 2 is negative 2. And then you can do negative 2 times 1 minus 3 to the 10th power. It's up to you, but the more that you let your calculator do, the more that you have to rely on your ability to use order of operations. Apparently, there's a way to use a graphing calculator for it. I haven't actually done it before, and I do got to look into it, but there's another way. Okay, solving a real-life problem. Let me drink water while I read this, because this looks confusing. Actually, I haven't seen something like this before, so let's take a look. You can calculate the monthly payment M in dollars for a loan using the formula. So I don't know what these represent here. L is the loan amount, and then you have a sum from 1 to, I guess, T years right here, and I is the interest rate to the K power, which is the things that you insert for that sum. Okay, yeah, I didn't know this formula, whatever. Sure. Calculate the monthly payment on a 5-year loan for $20,000 with an annual interest rate of 6%. So it looks like this would be your L. This is your I, but we have to use the decimal equivalent. 5-year loan, meaning T goes up to 5 there. Oh, the T is in months. I didn't know. Oh, monthly payment. Monthly payment. Got it. T is 5 times 12, which is 60 months here. So we are... Oh, and I is in months as well. The 6% has to divide by monthly. Got it. Okay, so we're dividing the 6% by 12 to get that 0.5% per month for 12 months total. And T is a number of months with 60. So let's keep all that in mind when we're doing the problems if they give us something that's not annual. Or whatever. They say quarterly payment. They say semi-annually. Whatever it is, daily payment. We're going to have to make sure that we divide and use the certain numbers there. So it's all a matter of substitution, y'all. And then this bottom part is, well, the interesting aspect about this is trying to come up with how this works as a rule. Because if we're using our geometric series formula, you have to recognize that this is still a geometric set because it's raised to this variable. But your first term, you'd have to substitute 1 for k, which is this. Your common ratio is also literally this thing when you combine these together. They're showing you that because that's the number that is the base for this variable. So we use both of those. We can substitute them in. They have a way of storing that into their calculator, which I can do as well if you want me to use that. And then they use their formula. It's the first term times 1 minus the common ratio raised to the nth power divided by 1 minus the common ratio. Now that is what goes in the denominator. That's the sum of those 60 months. You divide 20,000 by those 60 months and you get this, 386. This is the monthly payment amount. That's a lot. It's a lot to take in, and I don't know how many problems like that we'll have, and we'll look into them when we get them. All right. That is the end of the lecture portion. Let's go into questions 1 through 4 on the vocabulary and core concept check. Number 1, complete the sentence. The constant ratio of consecutive terms in a geometric sequence is called the common ratio. That's a lot like what we had to do in section 6.2, where they mentioned common difference as the first answer there. Number 2, in writing, how can you determine whether a sequence is geometric from its graph? It needs to be exponential in nature. That's all I'll say about it. It's a curve. It's nonlinear and it's a curve. I mean, there are other things that are curves, so I want to make sure you're not thinking of it like a quadratic. Exponential has that like asymptote appearance, but of course we are starting from just the first term. But it's exponential in nature. It features the common ratio as you multiply by something over and over. Complete the sentence number 3. The nth term of a geometric sequence has the form a sub n equals. Now this is that rule basically. You want to take the first term and multiply by the common ratio n minus 1 times to the n minus 1 power. And 4th on vocabulary, state the rule for the sum of the first n terms of a geometric series. This is where the first n terms is finite, and that's all we're referring to here. And this is just recalling formulas before you actually have to use them. So a sub 1 times 1 minus r to the n power over 1 minus r. Again, I can't get too deep into the whole how this comes to be. I mean, in proof form, I can do that, but as far as instant recall for a test, this is one you'll just have to know. I mean, as a teacher, listen, I haven't seen this formula in a year. And I mean, as a teacher, I'm expected to know it. But all I'm saying is I haven't seen this formula in a year because I haven't taught IM3 for a while since recording this video. And it's the only time that I get to use a formula like this. Actually, it's been a couple years. Yeah, eventually you know it. Eventually you do it. It's the one that you have to know. Everything else you can build off in its own way. So I guess we'll say it like that. All right, guys. Listen, you can be given the formula as well, right? A teacher can give you a formula for a quiz or test, but study it up, get it done. We're good to go. We're going to start with numbers 5 through 66. Well, we're going to start with the problem set, starting with number 5 and moving forward. Go ahead and find this PDF and download it. Use whatever you need to get this thing started. Let's go ahead and get going. In exercises 5 through 12, tell whether the sequence is geometric and explain your reasoning. We are looking for a common ratio for these. So on this first one, now they do ultimate larger tests with them. I'll explain them out loud, especially if necessary. Sometimes you work from the smaller numbers first and see what you're doing. Like if it has a common ratio, you're multiplying by the same number over and over. You can also say it through division, but you have to ultimately express the multiplication. Like for instance, I'm dividing by 2 here. These totally look like we're dividing by 2, and if you know half of 96 is 48, you're all good to go. You're all good to go. So your common ratio is 1/2. That does make it a geometric sequence. Now, why is it 1/2? Because 1/2 is what you're multiplying by going from one number to the next. It's not 2. It is 1/2. That does make it geometric. Number 6. Same thing. Are we dividing by the same number? And you can start with division to mention it, like I said, but ultimately come up with that common ratio as what you're multiplying by, in which case it's probably a fraction. If I look at the smaller numbers first and go like, hey, I'm dividing by 3. Is 81 divided by 3 27? A lot of people will know that and say yes. This one might take a moment longer or shorter. That's pretty quick multiplication. You can multiply by 3 upward, and it does work. Dividing by 3 downward also works, which also means you have a common ratio of 1/3. This is a geometric sequence as well. Now, what would the book do? Because I didn't bring that up. They would be dividing a term by the one before it. 48 divided by 96. 24 divided by 48. If you use the calculator, the decimal you'll get is literally 0.5. But they all reduce as fractions as 1/2. And these would be 0.3 repeating, which is a fraction of 1/3. But divide a term by the one before it. Number 7. 2, 4, 6, 8, 10. If it's arithmetic, it's not geometric. And that's exactly what this thing is here. This is arithmetic. It has a common ratio. What did I just write? It is arithmetic because it has a common difference, not a common ratio. So, not geometric. The reason could just be no common ratio. I can confirm that just by saying because there's a common difference. You're adding 2 each time. That's great for arithmetic sequences. That was not the question at hand. You're not multiplying by the same thing over and over. Otherwise, you can talk about it, and I'll talk about it with this problem here, even though it has the same effect. This one is also an arithmetic sequence because it has a common difference of 15. And if it has a common difference, then it cannot, therefore, have a common ratio. Unless your common difference is 0 and your common ratio is 1, because it's the same number over and over. But I don't think we're talking about those. Let's put it this way. 5 times 4 is 20. And if it had a common ratio, that means I should be able to multiply this thing by 4 to get 35. Nope. 20 times 4 is not 35. Therefore, it's not geometric. That's another way to determine that. So it's kind of up to you how you want to support it. Listen, the book would be doing 20 divided by 4, or 20 divided by 5 to get 4. 35 divided by 20 to get 7/4, which is not 4. And then once it breaks, you don't need to show all of them, personally. Once it breaks, it's not a common ratio. If it's not a common ratio, it's not geometric. Number 9, we start to hit some decimals, and ones that I believe could be geometric. This thing probably just misses the boat. Let's see what they're going to say here. So I got 0.2, 3.2, negative 12.8, 51.2, and negative 204.8. Never mind either way. This one, you could do division to figure these things out, but this one is times 16. And then it's times negative 4. This is kind of weird because I think they're just missing a term between these two. Because there was something else I was going to mention about them. Anyway, it's not geometric. The interesting thing is it has a common ratio everywhere except for from the first to second term. If you had the term in between, which would have been negative 0.8, because if I multiplied everything by negative 4, negative 0.8, and then that times negative 4 gives you 3.2, and that would have worked out. This is all that's missing here. If you got that one in there, it would be geometric. The thing I was actually going to call out was the alternating signs. If signs alternate, positive, negative, it has potential for geometric, and that's something I'd look into because it has a negative common ratio. But these two did not alternate. But not only that, the size difference was there. But times a couple negative 4s here and here, boom, you got it. Not apparently for this one, though. That's not there, so we don't got it yet. Little weird kind of way they constructed the question. You don't generally see one like that, but we did here. Number 10 is possibly an example of one that actually is geometric, though. So, alternating signs, that's not a check, but as long as it doesn't break that pattern, then, well, it's possible. And the question becomes, this time I'll actually do the division. Let's do negative 1.5 over 0.3. That's negative 5. Let's do 7.5 over negative 1.5. That's negative 5. Negative 37.5 over 7.5. That's negative 5. If you're asking if I'm doing that in my head, the answer is yes. But I'm also more so confirming that I'm expecting negative 5 as an answer. This one I wouldn't know off the top of my head. I'd have to work it out slowly. But I'm going to guess that's negative 5. A couple negative 37.5s in a row gets you 75, then 150. Yes, that does work. So it is negative 5. So these all check out. This does make it geometric because of that common ratio. But of course, what I would probably look into do is once you know what 1 multiplies by, you can also just write times negative 5 over and over and see if it works. I'm missing my ... there. Number 11. Okay, you don't need common denominators for common ratios because multiplying says forget the rules of common denominators and such for fractions as long as you're multiplying by the same thing. I really seek the top and bottomness of these as long as nothing's reducing as fractions. The top I'm just multiplying by 1. The bottom I'm multiplying by 3. That's times 3 times 3. And that's true. This is a times 3 scenario. So what am I really multiplying by? 1/3. Dividing by 3, right? That makes it a geometric sequence. And then number 12, also in fraction basis. I think we're multiplying by 4 on the bottom and 1 on the top. That would make this same thing have a common ratio. The common ratio would be 1/4. Now, if you followed the book's way of doing this, then they would probably be dividing one number by the other, which honestly gets a little bit weirder for my taste than using what I did here. But, you'd be doing 1/16 divided by 1/4, which is also the same thing as writing it this way, which is the same as multiplying by its reciprocal, which is 4 over 16, which reduces to 1/4. That's a lot of work just to get in that scenario. Instead, I'd work toward numbers that I know to multiply if it's not so much of a bother. And this wasn't. Times 1 on bottom, times 1 on top, times 4 on bottom. Common ratio is 1/4. Sequence is geometric. So we sandwiched some geometric sequences on the front and back, on the beginning and end, with some that were not geometric in the middle. Okay, number 13 on writing equations. We got to write a rule for the geometric sequence with the given description. Now, this is just exercising your formula usage. So part A says the first term is -3, and each term is 5 times the previous term. That's common ratio speak. So your rule is the value of the nth term is the first term times the common ratio raised to the n minus 1 power. Nothing to simplify, which is one way that this section could be a little bit faster than our arithmetic sequence stuff. Only I have a lot bigger numbers to calculate, so maybe not always, because I don't have to simplify more than this. I'm going to leave it like that. Part B, the first term is 72. That's our a sub 1. And each term is 1/3 times the previous term. That's literally, once again, your common ratio. So no difference in what I'm writing here. Just like that. All good. The only thing I want to state is that this one could be written without parentheses, and this one must be written with parentheses. Positive integers don't necessarily need parentheses because there's no order of operation precedence. Fractions require it because we got to raise both to this power, and so do negative numbers. I'm going to use parentheses regardless, unless it's a positive integer and there's no first term other than it being a 1. Maybe a negative 1. Number 14. Compare the terms of a geometric sequence when r is greater than 1 and r is between 0 and 1. Now, if you followed me on section 7.2, the layout of these questions are very similar to what they did with the arithmetic things, especially if you saw these questions I'm doing. Now, if r is greater than 1, then your numbers will increase. But if the numbers were negative to begin with, I guess I could say absolute value increases. So when r is greater than 1, the absolute value of your terms increase. And I'll tell you what I mean by absolute value. When r is between 0 and 1, the absolute value of your terms decrease. Okay, couple things. For arithmetic sequences, we talked about common difference. We either talked about greater than 0 or less than 0, because if we add numbers, if your common difference is greater than 0, like +5, +5, etc., then the numbers were getting bigger straight up, and less than 0, we're subtracting over and over, your numbers got smaller. They're not talking about negative common ratios right now, but when you have a number that's greater than 1, you multiply by a number greater than 1, the numbers get bigger. Whether they're bigger positives or bigger negatives, they get bigger in their direction. And when you multiply by a number between 0 and 1, they become a fraction, 1/2 or whatever. They become smaller from either direction. We won't multiply by 0. We could multiply by 1. You'll even see some negative ones, but there's that. Now, why did I say absolute value? Because what if your list was -2, -6, -18, -54, and I'm multiplying by 3 each time? My common ratio here is 3, positive 3, not -3. Joe, my r is bigger than 1, but are my numbers getting bigger? The negatives are getting bigger, but the numbers themselves, -54 is smaller than -18. You have to remember that. A bigger negative is a smaller value. So that's why I said the absolute value, 54 is more than 18, so it's a bigger negative, but so that's why I wanted to say absolute value for those. And that's why they didn't want to talk about negatives, because then signs alternate, and then there's not a consistent answer. All right, and exercises 15 to 22, write a rule for the nth term of the sequence, and then find a sub 7. Classic case of something you could have done even back in IM1, and I forget if we did problems like this back in 7.1. It's a couple sections ago. I'm already forgetful. Okay, so for this one, our first term is 4, and our common ratio, again, I'm not going to be cute about it, it's 5. We're multiplying by 5. We're not testing whether it's geometric or not. It is geometric. So this is 4 times 5 to the n minus 1 power as a rule. This allows us to find the value of any term just by straight up substitution. Now, this a sub 7 is 4 times 5 to the 7 minus 1 power. It's best that you write this as 4 times 5 to the 6th power before you go to the calculator, because you might mess up some order of operations things there. So notice that every time we are doing to the 7 minus 1 power, because it's a sub 7. So I'm just probably going to write it to the 6th power each time. And then I can do that straight up. And I'm getting an answer of 62,500. So 62,500 is the 7th term. Now, the 7th term is not very far away from what we had in our list, and that's going to be true for all of our sets. So it wouldn't be totally wrong for you to just take your 4th term of 500 times, what was our common ratio? 5 times 5 times 5 times 5, and we got the same answer there. But go with trusting how the rules work. That way we can use them in the future whenever necessary. So try and substitute those in. If I can do one mentally in my head, I might go for it. Number 16, 6, 24, 96, 384. First 4 terms are written there. We have a common ratio of 4 with a first term of 6. It's a positive 4. So your rule is 6 times 4 to the n minus 1 power. If we want to find a sub 7, we're going to have to substitute 7 in for n. So it's 6 times 4 to the 7 minus 1 power, or 6 times 4 to the 6th power. Now again, let your calculator do the work for you. What I mean by that is don't do 6, well, I take it back. The 7 minus 1 portion we did in our head. But don't try and do 6 times 4 first and then raise it to the 6th power. You're going to get a different answer. Your order of operations says you need to raise to the exponent first and then multiply. So let your calculator do it. Just type in what it shows there. Remember, this would be a different answer because this raises to the 7th power and then subtracts 1. That's not the answer. What you would have to do here is wrap this around parentheses if you're using a calculator with this kind of math print on it to get that matching answer up there. So I'd rather just say 7 minus 1 is 6. That is significantly easier to work off of. It also describes why we do the minus 1 because we start from the first term. Number 17. This time we're dealing with a common ratio that is of some form fraction because we are dividing, which means we're multiplying by a fraction. Check the smaller numbers to see it. 28 divided by what is 14? 28 divided by 2. So we are multiplying by 1/2. Our first term is 112. Our first term is 112. Our common ratio is 1/2 or 0.5. So your equation, I kind of want to write the rule over here, is 112 times 1/2 to the n minus 1 power. So if we find the 7th term, that's 112 times 1/2 to the 7 minus 1 power to the 6th power. Now, if I were to just do this in my head, 14 divided by 2 is 7. 7 divided by 2 is 3.5. 3.5 divided by 2 is 1.75. So that should be the answer. I'm going to write it before calculating it. But if I go to the calculator, keep in mind you do need parentheses around that 1/2. Otherwise, things can get screwbally. So 112 times 1/2 to the 6th power. And I should get 1.75. There it is. Okay. Number 18. Looks like we're dividing by 5, which means we're multiplying by 1/5. Now, once again, I actually didn't look at the smaller numbers. I looked at the bigger one. Once you find one set, they should all apply because this is all geometric. So your first term being 375 and your common ratio being 1/5 based on what we're doing there, like 3/15. Okay, I'll just write divided by 5 up there to support it. Your rule is a sub n equals 375 times 1/5 to the n minus 1 power. And 1/5 is also 0.2. But for the most part, you're going to want to write decimals. Now, there are times where I will stress that you should be writing fractions within your answers, especially if they present fractions. Case in point, look at numbers 19 and 20. So if I were to come up with the 7th term, here's the thing. We will be obviously substituting 7 into here. And if you use your calculator, it would give you a decimal answer. I'm going to first do this in a way where, times 1/5 times 1/5 times 1/5. I'm going to do it practically first or recursively by coming up with those next 3 terms right here, but using decimal form. 3 times 1/5 is 3/5. 3/5 times 1/5 is 3/15, and 3/15 times 1/5 is 3/75. So that could be your answer. You could write it as 3/75, and that, in a lot of ways, I like that answer more than the decimal. Now, I don't know what 3/75 is as well. Oh, that reduces. Hold on a second. Wait a minute. No, that's not 3/15. I apologize. I messed up. That's not good. Whoops, I was typing Z's. That would be 3/25. My bad. I was like, why does this reduce now? So 3/125. There we go. So a sub 7 is 3/125, which is an even weirder decimal answer than 3/75. 3/75 is actually fine. That would be 0.04, I think. I don't know this one. So let's do 3/125. Oh, 0.024. I guess not bad. But still a weird decimal. That's an answer. Now, if I did 375 times 1/5 to that answer, you'd still get that to the 6th power. And you can convert to fraction form, and it gets you that same thing. So it's kind of up to how you write it and kind of up to what you're doing. As I stated, obviously, we're using our formula to calculate some of these answers, but fraction answers ain't all that bad. That's all I'm going to say. On these problems, I kind of expect that we should be writing fraction answers, just because they present fractions to begin with. Number 19. 4, 6, 9, and 27/2. Now, interestingly enough, this turned into a fraction, but the numbers aren't getting smaller. They're actually getting bigger. 4 times what is 6? 6 times what is 9? This is where you might want to dive a little bit more into doing the division. A term divided by the one before it, and that's 3/2. I'm going to leave it as the fraction instead of the decimal, especially since these are fractions right here. So your rule, your first term is 4. So a sub n equals 4 times 3/2 to the n minus 1 power. The 7th term, again, you can do a substitution. 4 times 3/2 to the 7 minus 1 power to the 6th power. Now on the calculator, again, I can convert to fraction form after doing my calculation. It'll give me a decimal to begin with, but I need to respect that the problem initially had fractions, so I'm going to live with a fraction answer ultimately. Strange decimal, the fraction answer as an equivalent is 729/16. Now, you can also do that by multiplying by 3 halves a few more times here. 27, so times 3 halves. 27 halves times 3 halves is 81/4. 81/4 times 3 halves is 243/8. 243/8 times 3 halves is 729/16. And that's what we get here. Number 20. These numbers are getting smaller. We go from 2 to 3 halves, and 3 halves is 1.5, but this gets a little trickier when it comes to common ratio. Once again, you divide a term by the one before it. And once again, as long as the calculator can give me a fraction answer, I'm going to go ahead and state what that is. So let's get the first term is 2. Let's divide 3 halves by 2, which is 3 halves times 1 half, which is 3/4. 3/4 is our common ratio, what we're multiplying by from one term to the next. So your rule is 2 times 3/4 to the n minus 1 power. Now your a sub 7 means we're going to substitute 7 into there, which 7 minus 1 is 6. We'll use the calculator. We'll convert it to fraction form, and we get, I can do it right from here, boom, 729/2048. If you're really curious about the decimal, you can go ahead and divide that. It's a number between, I don't know, it's around 0.3, I don't know what it is. Probably around, somewhere between 0.3 and 0.4. I don't know what it is, but go gung-ho, guys. Number 21, this one has decimals. So listen, I'm going to write it as decimals. I won't use a fraction this time. You happy? As far as common ratio goes, see, these decimals aren't going to get more decimally because the common ratio actually looks to be an integer. Notice that the signs are changing. That means your common ratio is negative. So you can divide 1 by the one before it. You might notice the 3.9/1.3. That's 3 times bigger. So this will be -3. So your rule is 1.3 times -3. Use them parentheses to the n minus 1 power. And our 7th term will be 1.3 times -3 to the 6th power. Please use parentheses around this when you do that negative portion, because you don't want to raise a negative number to an even power and get a negative answer. This should be a positive answer, being the 7th term. We'll talk about confirming that. So positive 947.7, and the decimal is fine. Now, should the 7th term be positive? Yes, the first and third terms are positive, second and fourth are negative, 7th is odd, just like first and third, it should be positive. Number 22, also alternating signs and also in decimal form, so we'll leave the final answer in decimal form. This is one where I'd be proud to use the formula rule again. This time, well, actually, hold on, I wrote that wrong. This also should have a positive 7th term because the first and third are positive as well. Your common ratio, I think we did this division a bit ago, right? Something like it at least. This is -5. So you have a sub n equals 1.5 times -5 to the n minus 1 power. So for that 7th term, raise it to the 6th power. And let me calculate this 1 second. Positive 23437.5. 23,000, y'all. Okay. All right. Let's do 23 to 30. On these ones, we're going to come up with the rule based on having a bigger term. Like the third term is 4, the common ratio is 2. This is some of those ones where, yes, I do want to kind of give the like a conventional way of doing these without needing to get too deep into formulas. For your formula, you need 2 things. Common ratio, we got it. and the first term. We don't got it. But listen, we do have the third term. Let me do a practical way first just to say, hey, these are pretty fine to do. I have the third term, y'all. I have the third term as 4. My common ratio is 2, which means I multiply by 2 this way. That means I divide by 2 this way. What's 4 divided by 2? What's 2 divided by 2? That's your first term. This is your a sub 1. So there's a way to do it. I'll go back and look at those every so often, especially when your terms are... All these terms are so small. The largest one you have is the 5th term. Now, how much you want to deal with fractions and negatives and things like that to make it happen, I get it. But you can always work backwards that way, guys. That being said, we have this rule, this formula. We can do this for the third term as well. A sub 3 is 4. And we can find a sub 1 by substituting 2 into here and 3 minus 1 into here. 3 minus 1 is 2. And you get 4 equals 4 times a sub 1, because 2 squared is 4. Divided by 4, you get a sub 1 equals 1. So our rule can be a sub n equals 1 times 2 to the n minus 1 power. What you would see in an answer key likely is just 2 to the n minus 1 power, which means you need to understand in that scenario that your first term... If they gave you this equation and they said, what is the first term? Well, you can substitute 1 and figure it out, but also you know that the missing number invisible in front is a 1. Now, they do want us to graph. I need to... If I'm going to be changing scales all the time, I'm going to attach the tall graph paper for these ones, guys. Are any of these negatives? We will have negatives, just not yet. Sorry, I'm copying and pasting a graph thing here. So, this is going to look a little weird with the black. Just bear with me on this one. I'll fix it on the next problem, okay? Let's get these scales. Oh, what are my 6 terms? My first term is 1. So 1, 2, 3, 4, 5, 6. These go up to 17. Therefore, I'll go by 2s here. 10, 20, 30. So my first term is 1, and then 2, and then 4, 8, 16, 32. I think I actually lucked out with that one. That could have been a lot worse. Sorry about that. There's my scale. Okay, let's move on to the next one. This is, once again, if we want to do that conventional way, we could. I'll go with the way they're going to do in the book here. A sub 3 is 27 and common ratio is 3. So your third term is equal to your first term times your common ratio. 3 minus 1 times, so 2 times. 27 is 3 squared, which is 9 times a sub 1, so a sub 1 equals 3. How else could have we found that? Your third term's 27. Let's divide by 3 a couple times. Divide by 3 is 9. Divide by 3 is 3. So your rule is going to be a sub n equals 3 times 3 to the n minus 1 power. First term and common ratio are both 3. So your first 6 terms are us multiplying by 3 over and over here. Start from 3. Times 3 is 9. Times 3. Times 3. Times 3. Times 3. Which means we got to change the scales to something pretty high. I'm going to get this graph thing again because I'm going to get rid of all that black that was in there last time. Okay, going up to 729. This is going to be a little tough for me to determine. This goes up to 17 here. I'm just going to go up so that this is 1,000. I don't think I have a really better way of doing this than that. Oh, you know what? 750. If I go by 2 50s here, I don't think I made this easier for me at all. That means these go up by 50s, though. I don't think I made that easier for me at all. But I did stretch this a little bit more. Okay. From 0 to 50, here's 3, just way down there. And so is 9. 9 is way down there here. 27 is about halfway from 0 to 50, just a tick above it. And then 81, here's 50, here's 100. So 81 is getting a little bit closer to 100 than not. Wait, I must have done something wrong. I'm sorry. This is 0 to 50, right? 27 is that more than halfway between like that. 81 is up here. There we go. 243, well, here's 250, so we're right underneath it. And 729 is a little more than 725, which is about halfway between 700 and 750. So it's about right there. Boy, that triples pretty fast along the way. And there's your graph. Ta-da. Yeah. Never been a fan of doing all these graph things with these ones. Listen, I get it. We got to do some graphs. But just, these have no relevance to me. The scales get really big, and I got to choose them. Number 25. Okay. The second term is 30. And your common ratio... See, these are ones where I really just... in my head, I'd really prefer doing it this way. If we're taking half of something over and over... Here's the thing. You might mess up, though. Because you might say take half of 30, that's your first term. No, we took half of our first term to get 30. So if half of something is 30, you got to double it to get your first term. Your first term should be 60. Now, as far as formula goes, your second term takes your first term times your common ratio once, and you divide both sides by 1/2. So times 2 times 2, and that's where you get 60. So your rule is 60 times 1/2 to the n minus 1 power. We are going to come up with our 6 terms here. Let's see how many decimals we get. And I'll write them as decimals. So 60, 30, 15. Okay, 7.5, 3.75, 1.875. I don't know if I did that right. 3.75 divided by 2. 3.75. Yes, 1.875. Okay, still positive numbers for our first 6 terms. This goes up to 17. I'm going to go by 4s so that this top one can be 60. This top, not the very top hash, but if I go by 4s, this is 60 and 40 and 20. So 60 is your first term. 30 is it's halfway between 20 and 40. It's actually right here. So we're going by 4s. Can you see the whole? You can't see the bottom. 7.5. This is 15. Excuse me. 4, 8, 12, 16. 15 is 3/4 of the way up. Yeah, nothing I do that's too pretty here. 7.5, 4, 8. It's right next to 8 pretty much. 3.75 is pretty much really close to 4. And then 1.875 is pretty much really close to 2, just under halfway between 0 and 4, so like that. Okay, number 26. The second term is 64, and we're taking 1/4 of each value to go from one term to the next. So we have to multiply by 4 to get the first term. And 64 times 4 is 256. Aha, I cracked that the first term is 256. But to set it up, the second term equals the first term times 1/4 once. So you divide both sides by 1/4 and multiply by 4, and you get your 256. So your rule is 256 times 1/4 to the n minus 1 power. The tricky part is, what are your 6 terms? Because that's what we have to write out. So we do have our first and second term already. 256 and 64. Divide this by 4. You get 16, 4, 1, and 1/4. Okay, that wasn't too bad. 1/4 is also 0.25. I guess this time I'll write it as the fraction. The tricky part's the scale. 256. If I made this 300, then I'd be going by 20s. So 100, 200, 300. I think that's my best fit. I could go by 16s. You know what? Let's go by 16s. That would make this 256 up here. That sounds weird. I know it does. But these have like multiples of 16, sort of, until the very bottom. But 256, this is 15 increments of 16. That's 240. And then this is 256 right here. So 256 is right at that top. 64 is 16 times 1, 2, 3, 4. So boom, I'm hitting those points exactly. 4, here's 16. Here's 16, so this is 1/4 of 16. And listen, the numbers were going to get small no matter what I did. This is even better than it would have been the other way. And 1 and 1/4, it really does shrink to basically an appearance of 0. But those are the points that you're going to be able to see. I'm missing points. What am I doing? 64, 16. Oh, I'm missing 16. 16, 4, 1, and 1/4. There we go. I was like, I'm missing terms. That was a rapid jump. All right. Number 27. All right, this is one where I'm more likely to just use their formula thing, right? Instead of dividing by 4 3 times from -192, which is fine, I'm just going to use their version of it. I don't know the answer off the top of my head, but I could get to it if I thought about it hard enough. Negative 192 is the first term times 4 common ratio to the 4 minus 1 power to the third power. 4 cubed is 64. So we get 64 times a sub 1. Divide both sides by 64. You get a sub 1 is negative 3. So your rule, that means all these will be negative, by the way. Negative 3 times your common ratio 4 to the n minus 1 power, like so. So your terms, this I might have to go to the calculator here a little bit, but we got negative 3, negative 12, negative 48. Here's this negative 192. Negative 192. Negative 768. And screw it, I'm going to the calculator. 768 times 4. Negative 3072. All right, there are the 6 terms. We got to get to negative 3072. We are going negative, period. So with that, the graph stuff that I'm attaching, you want to use the bottom, the 4th quadrant this time. So I'm copying and pasting here, but we're going down. For 3000, negative 3072, I'm going to make this get to 3000, negative 3000 down here. That means this negative 2000, negative 1000. That means I'm going by 200 each time downward. So let's start from, well, I can start from negative 3. I'm going by 200 each time. There's no chance in heck that you're seeing anything else other than negative 3 just down there. Same with the negative 12. This is negative 200 right there. I don't know. We're still looking at a small percentage, like 5% of that number. Negative 48 goes about halfway. Wait a minute. About a quarter way to negative 200. Still very small. Negative 192 is just about negative 200 right there. So now you're finally seeing something. Negative 768, 200, 400, 600, 800. It's a little bit below or above 800. Negative 800. And then negative 3072 is a little bit more than negative 3000. Actually getting a little closer there. Like that, probably. All right. They asked me to graph, so giving them their graphs. Number 28. A sub 4 is negative 500, and R is 5. Once again, this is an easier division. If we're multiplying by 5 as we increase, we divide as we decrease. Check this out. 4th term is negative 500, right? Divide by 5 to the 3rd term. That's negative 100. Divide by 5 to get 2nd term is negative 20. Divide by 5 to get the 1st term is negative 4. So we should get negative 4 now. Let's try it out. 4th term is the 1st term times 5 to the 3rd power. 5 to the 3rd power is 125. Divide by 125, you get negative 4. So your rule is negative 4 times 5 to the n minus 1 power. Now I stated those numbers out loud. Let's bring them back. So negative 4, negative 20, negative 100, negative 500. Multiply by 5 a couple times more. Negative 2,500 and negative 12500. Negative 12,500. Okay. Which stands to reason that we might as well go by 1,000s on each of these sets of points here. Because, yeah. So this would be negative 5,000. This would be negative 10,000 and negative 15,000. Negative 4, these are going by thousands. Are you really going to see negative 4 compared to anything else? No, not even negative 20. These are just very, very small. That's negative 1,000 right here. Negative 100 is only 1/10 of the way to negative 1,000. Even then, that's very small. Negative 500 is only halfway to negative 1,000. There, we got some substantial difference. Negative 2,500 is halfway to negative 5,000, so that's here. And then you get negative 12,500, which is halfway between negative 10,000 and negative 15,000, which is right there. So it is exponential. Can't you tell? It is, well, looks it at that point. You can't tell when it's flat there towards 0, toward the asymptote. All right, a couple more. We have some fractions. They have negative common ratios as well, which will mean we're going to have to alternate signs. That means for my graph, I have to have both the first and fourth quadrants on it, okay? So at number 29, your fifth term is 3. Common ratio is negative 1/3. That means the numbers get smaller as we go. That means if we work backwards, we'd have to get bigger. If we're multiplying by negative 1/3 this way, then we're multiplying by negative 3 the other way, just so you know. So that also helps when it comes to solving this stuff. Your fifth term is 3. So you take your unknown first term and multiply by your common ratio, 5 minus 1 times, 4 times. Negative 1/3 to the fourth is negative 1/81. So we are going to multiply both sides by negative 81. That's your ultimate thing when it comes to finding that first term, which is negative 243. So your rule is going to be negative 243 times negative 1/3 to the n minus 1 power. If we take a third of each number, moving forward here, we can get these terms. The signs will alternate. We know the fifth term will be 3, so we start from here. Second term, third term. Oh, wait, hold on. Now I did something wrong. This isn't negative. Hold on. This isn't negative here. I take this back. This is positive. This is positive. So let's do that. It's good that I knew what the fifth term was. So yeah, positive 1/81. My bad. So second term, fifth term, or third term, fourth term, fifth term. There's the positive 3. Sixth term. All right, they're all integers. Their signs do change. 243 is the largest I need here. So when it comes to scale, I'm thinking about it. I'll probably just go by tens. If I go by 15s. Wait, I would if I go by anything in comparison, it would be less than 10 actually. If I went by 8s. Oh, how about 9s? Hold on a second. Because a lot of these are multiples of 9. Is that too weird? What's 9 times 15? 9 times 30. Oh, I can't even go by 10s. I need to hit 243. Then what do I need? 15's also weird. 243. Hold on. I'm just going to pause to think of a good scale. Apologies on that. Let me think of a good scale, then I'll come back to you. All right. I couldn't come up with anything great, at least not without hitting weird fractions that'll make you pause and go, what are you plotting? I'm going to go by 20s. At least it'll hit my 240 that way. So I have 100, 200, 300. At least it'll hit it. Nothing's going to be great, but at least you understand these numbers a little more, right? So 243, they're going by 20s. So 220, 240, 243 is, somewhere between 240 and 260. Now it goes to negatives. It goes to negative 81, which is, negative 20, negative 40, negative 60, negative 80. Negative 81 is right near that negative 80. And then 27, 20, 40, 30, and 27 is right below. Oh, I need to move this one over. 27. Negative 9 is less than halfway between 0 and negative 20. It's about halfway. Who am I kidding? 3 is getting a little closer, and negative 1's a heck of a lot closer. So there's kind of an alternating thing. These aren't exponential functions anymore because they keep changing signs, but you still plot them. All right, number 30. The only thing I'm hopeful for here is that I can get a good scale for my graphs, my points that I plot. So 30. We have a fifth term of 1 and a common ratio of negative 1/5. I'll tell you what, if there's a good reason actually to do that backwards, listen, I'm going to do the backwards approach thing this time. If there's a good reason to do it, it's because I need all 6 terms anyway. So why not just say, hey, guys, this is my fifth term. Multiply by negative 1/5 you get here. Divide by negative 1/5 is times negative 5. So let's just work backwards anyway and get these numbers there. And boom, I have my first term. I mean, roll backwards. I didn't even really think about that for previous questions, but yeah, I got my first term. I have my common ratio, and we have that there, right? Now, you could have done all the other stuff we did on the previous questions. You'd get a first term of 625. So there are the terms. They do alternate signs, so we are going to have to work both top and bottom. 625 is... I can't even go by 20s this time and make that justified. Some multiple of 5, right? 50s? I'll probably have to settle with 50s. How about 25? No, that one fits. Okay, I'm going to go by 50s. So this is 250, 500, 750. All right. Going by 50s. Okay, so for this one, I really just need to fit kind of this set right here. 625, 550, 600, 650, 625 is right in the middle. Yeah, this will work. Negative 125, negative 50, negative 100, negative 150, negative 125. 50, 25. Negative 5, getting pretty close to that. Well, it's a tenth of the way to negative 50, so I really, really, really got to push it in there. 1 and negative 1/5. You ain't going to see the difference between those two given the scale. So there are the points for that graph. Okay, let's do numbers 31 and 32 in error analysis. Describe and correct the error in writing the rule for the nth term and the geometric sequence for which a sub 2 equals 48 and r equals 6. So we're going to use this for both questions, and let's see what they want to say. Number 31, they use their rule with the first term times r to the n power instead of to the n minus 1 power. It's something they even warned about in their lecture portion. They only raised their common ratio to the nth power instead of the n minus 1, n minus first power, n minus 1 power. I'll just say n power. That was their mistake. Whatever they did the rest of the way is probably correct work, but from the wrong formula. So we got to use a sub n equals a sub 1 times r to the n minus 1 power. They're talking about the second term. This is where I could tell you right now the first term is 8 because the common ratio is 6. So the second term of 48 is the first term times 6. Just once divided by 6, you get a first term of 48. I guess it's not too hard to do that. So your rule is a sub n equals 48 times 6. Oh, excuse me, 8. 8 times 6 to the n minus 1 power. Oh, why did I write 48 then? That's why I wrote that. All right, 8 times 6 to the n minus 1 power. Fix Mr. Robinson's mistake, why don't you? He just wrote a 48 when he said 8. Number 32. They swapped, well, this was the same kind of mistakes they did on the arithmetic stuff as well. They swapped their common ratio and your a sub 1 terms in their formula. Their formula has r and a sub 1 swapped. I've never seen that happen. Honestly, I've never seen, I'm not just saying in terms of writing, I've never seen someone swap those things before. So now in terms of correcting it, I'm not going to say much more than what's written up here. It's still the same problem. So let's just use that again. All right, next exercise is 33 to 40. Write a rule for the nth term of the geometric sequence. This time we have two given terms. And we kind of do a system of equation version of solving here. There are other ways we can talk about it. I mentioned it in the lecture portion. I'll probably just leave it to their system of equations. I'm going to solve half of them using the substitution method and half of them using the elimination method. The book uses substitution method. I've done both before in the past, so I'm going to continue doing that. So the two equations I can write, my first one is 1792 equals, and then we have your first term times your unknown common ratio as well, right, to the 5 minus 1 power. So I'm straight up going to write to the fourth power right here. And 28 equals a sub 1 times r to the 2 minus 1 power, so r to the first power. Now, you want to get an a sub 1 by itself because a sub 1 will always be a constant you can substitute in there. So let's isolate this one by getting a sub 1 is 28 over r. This is using substitution. 28 over r will now take place of the a sub 1 up here, and we'll have an equation that now says 1792 equals 28 over r times r to the fourth power. This r to the fourth power divides by this r, and you're left with r to the third power there. So now we can divide both sides by 28. 1792 divided by 28 is 64. So now we'll have r cubed equals 64. You take the cube root of both sides, you'll get r equals 4. It's not a plus or minus 4. It's just r equals 4. If r equals 4, you can substitute r into here and get a sub 1. A sub 1 is 28 over 4, which is 7. And you have your common ratio in your first term. That's your goal for coming up with the rule for these, always 7 times 4 to the n minus 1 power. Are there other ways to do it? Of course. I mean, not, also elimination method and stuff, but this is something we've done in the past. We're just using it for now geometric sequences. So I feel like there's not a lot I need to teach here given what you had done in the past with it. I know it was probably more in a first semester environment. So we're reliving these, and maybe that's why we get to practice them. Your first term here is 11. That's awesome. Don't overthink this problem, guys. You have a first term of 11 already. So let's use that. Our rule is first term times common ratio n minus 1 power. We just need the r now. So now we can say, let's just substitute them into here. 88 equals first term times r to the 4 minus, n minus 1 power there. You divide by 11, and you take the cube root of both sides. You get r is 2. So your answer here is a sub n equals 11 times 2 to the n minus 1 power. Okay, number 35. You also have the first term. Whenever you have the first term, use it. First term is -6. Fifth term is -486. So, given that -486, so I'm not even doing, listen, I said I'd do elimination, substitution, whatever. If I have the first term, I'm not using one of those methods. Well, sort of. I'm going to take my first term, though, and plug it into the equation. We just need to find r based off this. This is the 5 minus 1 power going on here. Divide by -6. You get r to the fourth. I'm not going to pretend like I know what that is. So I'm going to 81. 81. And here's the thing about this one. It says write a rule for the nth term. That's the interesting part of it. They didn't say write the rule. This one actually has more than one answer. You take the fourth root of this, you get plus or minus 3. There are two different answers here. One answer is a sub n equals -6 times 3 to the n minus 1 power. Another answer is a sub n equals -6 times -3 to the n minus 1 power. Just think about the fact that the only two bits of information you have are the first and fifth terms. They're both odd numbers. They both have negative values. That means the signs could have stayed the same. They could have been negative the whole time, or they could have alternated. Negative, positive, negative, positive, negative. So we don't know which one it is, so either answer is acceptable, given that this is all you have. If they said r can only be positive, that would be one thing. If they said that signs couldn't change, that would be one thing. But in these cases here, that works out, either or. They said write an answer, either of those work. Number 36, we don't have the first term anymore, so maybe we have to work a little bit more based off of systems. This time, let's use the elimination method. The elimination method for exponential equations comes in the form of dividing out your a sub 1's. So to the 6 minus 1 power here, and over here is to the 2 minus 1 power. So if I divide these ones straight up right now, the a sub 1's go away. I prefer elimination for these. And you get r to the fourth equals, and divide these, you get positive 625, and take the fourth root of both sides once again. Well, it's plus or minus 5, but once again, there are two different answers you can get here. Now, I haven't found my first term yet, so you got to substitute it into one of these, like this one here. R can be either plus or minus 5. So a sub 1, r plus or minus 5 times a sub 1 can be -10. When you divide by plus or minus 5, a sub 1 is either positive or -2. Now, it depends. Oh, and that's interesting as well. If you have... Okay, there are only two answers you can put. But you have to plug in the right one with the right set. If I plug in a positive 2, then my signs have to alternate, because I have to go from positive to negative. So I couldn't plug in a positive 5 here. I'd have to plug in a -5. I haven't really seen a problem like that before, that I had to do that, because I haven't solved systems with them before. If I do a -2, the signs have to stay the same, because the second term has to be negative like the first term is. So this or that. It's not just plus or minus straight up. You have to put the -2 with the positive 5 or positive 2 with the -5. Kind of interesting that if you choose one versus the other, that's what would be happening. And second and sixth terms are both even. Therefore, it's cool that they can alternate and get there. Number 37 has the second and fourth terms here. I'm more inclined to do a little more, I don't know, guess and check. You know, every so often, you got to play the ball as it lies and make more sense of your problems, guys. This time I want to do a little bit more of kind of the filling in the blank things, right? I have my second term here. I have my fourth term here. I need my first term. I need my common ratio. I'm dividing by 64 the whole way. That means I'm dividing by 8 twice here. That means I'm multiplying by 1/8. So there's my common ratio, which means this needs to be 8 times more to get this one. 64 times 8 is, I think, 512. So a sub 1 is 512, and common ratio is 1/8. Those are the two things we need there. Your rules, a sub 1 equals 512 times 1/8 the n minus 1 power. You know what I left out, though? This is an answer. Is it the only answer? No. Because these could have been negative 1/8. Therefore, this could have been a negative 8 for negative 512. So keep in mind, if it skips, if it goes an even number of things you multiply, this is why you should do this algebraically, honestly. Another version of this answer is 512 could have been negative and 1/8 could have been negative. I probably shouldn't be doing that anymore for your sake. My sake, I don't care. I'll do it as much as I want. For your sake, I should probably be doing the formulas, but I wanted to reveal at least one more of those. Because on number 38, I get at least one more opportunity. Oh, guys. Listen. How do I write 38 other than the answer itself? They gave us the first and second terms. The first term is 1. The second term is 1 times 49. So, guys, now, this is a way to write the answer. Whoops. I would prefer to write just 49 to the n minus 1 power. There's not much to say on this one. You know, if you bog yourself down with a system of equations and furthermore get the answer wrong, I don't have much sympathy for what you're trying with the problem. If you recognize a problem for what you have, use it. We have the first term. For all intents and purposes, we have the common ratio as well. We just went from the first to second term. I don't know what else to say. That's the answer. 1 times 49 is 40. Well, 1 times anything is that something, so we can write it like that as well. And by the way, I apologize if it sounds like I'm saying something in a condescending tone. I'm not. What I'm stating is, make sure that you really, this isn't even think outside the box. Make sure you don't hog tie yourself down to processes. I hear it too many times where students memorize, and that's not learning. Make sure that you're learning what's happening going on, and you can be efficient. You avoid mistakes. You can be faster with it. You can make sense of what's going on. And that's what I want to supply you with here. This is a solution guide where I get to talk you through my process and how I became what I am. How I would work this out if I were seeing it for the first time, which I very much am. All right, this is one I really don't mind doing system things, and same with number 40. Those seem totally fine for it, so let's go ahead and work them out. Let's use substitution this time. So we'll have the value of the second term is the first term times the common ratio 2 minus 1 times, so to the first power. And the value of the sixth term is the first term times the common ratio to the 6 minus 1 power to the fifth power. This one we can rewrite as a sub 1 is negative 72 over r. So when you substitute that into this formula down here, we'll get negative 1/18 equals negative 72 over r times r to the fifth power. Divide that r with that r to the fifth, you get r to the fourth. Divide by negative 72. That's the same thing as doing negative 1/18 times negative 1 over 72. Like that. Big number. It's the same thing as whatever 36 squared is on bottom. And 1296. Let's see. 36 times 36. I believe we should be getting 1 over 1296 there. So r to the fourth is positive 1 over 1296. And when you take the fourth root of both sides, you will get a plus or minus. And that should be 6. So 1/6. Plus or minus 1/6. Now there's a plus or minus involved given the even root that we're taking. If we substitute 1/6 into this, a sub 1 is negative 72 over plus or minus 1/6. Remember that dividing by 1/6 is the same as multiplying by 6. And 72 times 6 is 432. So a sub 1 is plus or minus 432. I'm going to make sure my answer makes sense in a second. And one thing I need to make sense of is that I keep the signs the way that they're supposed to go. So if I use positive 432, I need to alternate signs because I need to make this become negative at some point. So that needs to multiply by negative 1/6 to the n minus 1 power. That's a version of the answer. And if I use negative 432 to begin with, then the signs need to stay negative, so I need to multiply by positives the entire time. And this makes sense of 1/6 being an answer. I started from bigger, and it just gets smaller as we go. I'm feeling it. It's looking good. Number 40. Let's use elimination. Second term is negative 48, and the fifth term is 3/4. So let's do negative 48 equals a sub 1 times r to the 2 minus 1 power, so to the first power. And 3/4 is a sub 1 times r to the 5 minus 1 power. We're going to use division here. Now, a couple things on division. Those cancel. R to the first over r to the fourth is r to the negative third power, or 1 over r cubed. Let's actually write it, we'll start r to the negative third. And this is negative 48 times 4/3. When you divide by 3/4, you're multiplying by 4/3. 48 divided by 3 is 16 times 4 is 64. So we have negative 64 here, and r to the negative third is 1 over r to the third. Switch spots here, you get r cubed is negative 1 over 64. That's multiplied by r cubed and divided by negative 64. And take the cube root of both sides, you get r equals negative 1/4. 1/4. I was going to say negative 4. Your common ratio is negative 1/4. It makes sense that the numbers are getting smaller. It makes sense that the signs are alternating. So your first term, you can take negative 48 equals negative 1/4 times a sub 1. Multiply both sides by negative 4. You get a sub 1 is positive 192. Hope that's right. So your equation, it's just one equation. A sub n is 192 times negative 1/4 to the n minus 1 power. Notice that the signs are alternating, and we go from an even term to an odd term, changing signs. So there's only one version of this answer we can do on that one. Okay. Numbers 41 to 46 say write a rule for a sequence with the given terms. And I'll tell you what, this layout is almost exactly what section 7.2 was when it comes to layout. I don't know how the word problems are going to change, but it seems like everything we're doing is very much like they were at the time. Now, I'm not going to get too deep into this stuff. If they give me, I'll write out the list of numbers. 4, 8, 16, 32. Those are terms 1, 2, 3, and 4. That's your first term, and 2 is your common ratio. So if we can spell that stuff out, we would get this as an equation. So I'll say them out loud. But we've been doing enough of these that we know what's going on with it, so I'm going to leave it be. Number 42. On all of these, we get our first, second, third, fourth terms. I'm only going to get the common ratio if it's I'm going to calculate it if it's hard to obtain. So 5, 15, 45, and 135. We have our first term and a common ratio of 3. So this is 5 times 3 to the n minus 1 power. On number 43, these numbers do go down like a division, and a division is multiplication by a fraction less than 1. So 5, 2.5, 1.25, and 0.625. Even if you have trouble with the last couple, a lot of us know that half of 5 is 2.5, so we're taking half of them. Half is our common ratio. Or 0.5. And I might want to write out 0.5 this time just because we had decimals. So if we have decimals here, maybe put a decimal there. I don't mind. 44 also is going down. We're going from, and I'm sure you can spell this out once you see the list, 48 to 12 to 3 to 0.75. Now, the ratio, we're dividing by 4, so that means that your common ratio is 1/4, but as a decimal, that's 0.25, which I'd prefer to write just because they have the decimal there. So a sub n is the first term times the common ratio to the n minus 1 power. I know I'm operating fast on those, but they're no different from how we began our problems very early on, so less work is probably more expected there. 2 more out of tables. Now we don't have the first term, so we do have the second term, which is pretty close enough. If I wrote this out as a list like that, that first term that's missing, let's just come up with the common ratio and work ourselves backwards to get it. We still have to write the equation. We just go to there. So based on what you can see here, we're multiplying by -2. So we divide by -2 going this direction, and we get a +6. That's your first term. So your a sub n is 6 times -2 to the n minus 1 power. That is this rule. And on number 46, I don't know if this is less obvious or what have you, but we're multiplying by a negative. 20. You can do 63 divided by -21, and you'll get -3. So you are multiplying by -3 as these increase. I'm not even bothering with the other ones. We know they're geometric. So we are multiplying by -3 going this way. So we'll divide by -3 going that way to get the first term, because this is the second term based off this n being 2. N being 1, we get a first term of 7. So your rule here is a sub n equals 7 times -3 to the n minus 1 power. Okay, now we hit our sums, and I believe we're going to get a lot of sums moving forward. We're basing everything off of a single formula here. So before I write this thing out, the series sum, the sum for a finite geometric series is a sub 1 times 1 minus r to the n power, all over 1 minus r. The book has some slight alteration in how the parentheses are written. This is how I just personally write it. Doesn't change the answer. So, number 47, we have sigma notation. We're going from the first to ninth term. And we have done a lot of geometric series rules so far. They have that n minus 1 power appearance to them. So this is going to be very helpful for you to determine the information. We need the first term, the common ratio, and number of terms. Based on what you see, that whole a sub 1 times r to the n minus 1 power, your first term is 6, your common ratio is 7. From 1 to 9, your number of terms is 9. We know straight up that we have that information, so we can write out the formula. We had it out. I didn't have to plug in anything there. I just have to now plug them into this formula here. So the sum of the first 9 terms of this set is the first term times 1 minus the common ratio to the 9th power over 1 minus the common ratio, like that. Now, there's some simplification that I prefer to do here before going to the calculator. For example, this is 6 over -6 right there. And let's figure out 7 to the 9th. And this is 1 minus... Ooh, I'm just going to keep it as 7 to the 9th for now because it's a kind of big number. This becomes -1. So whatever you want to do with that ultimately, right? So I can go to the calculator after that. This was the big number I was talking about. So the opposite of 1 minus 7 to the 9th is basically what I'm going to do inside there. And I'm getting this number here, which is 403,53606. Now, it's worth mentioning what kind of answers you do expect sometimes. If you notice, we don't have the sequence, but if you notice, the first term is 6, the second term would be, I guess, 42, and bigger is positive numbers. Our final answer should be positive. We're just adding a bunch of positive numbers over and over. I know negatives are thrown all into the mix. I got a negative here multiplied by what becomes a big negative there, but it should turn positive. So if there are mistakes to be had, it's often with your order of operations in your calculator or with the way you're doing certain things there. So just make sure your answer makes sense in what you do. If I got a negative, something went way wrong. Probably a miscalculation and just one set of parentheses are needed, but just make sure you address whatever it actually is you have to address. All right, this is once again a geometric sequence explicit rule, so we can pull out the first term, common ratio, and from 1 to 10 is 10 terms. So we're going to find the sum of the first 10 terms here by doing 7 times 1 minus r to the n power over, r is 4, all over 1 minus r. Now, this is one that unfortunately does not do a lot in terms of simplifying this guy here, because 7 over -3 doesn't reduce. Interestingly enough with that, I'm just going to write it like that just because the numbers get too big. But these are all integers that are adding, so I'm guessing this number up here must be divisible by 3, otherwise this wouldn't work out. Now, notice that I still did that reduction anyway. I think it's super important to do that before jumping to the calculator, just because you don't want to do this. 1 minus 4 to the 10th over 1 minus 4. The problem with this is I just disrupted my order of operations. I need to put 1 minus 4 in parentheses, basically. It's better if I put negative 3, and to me, better if I get to reduce fractions and do numbers however I can. So it is an integer value. It's positive. I expected both of those just based off the nature of what the original set was. It's big. All of these will be pretty big. Not always. But based off what we're doing and what we're actually adding together, we're adding 7 with 28 with 112 with, and the numbers just get bigger, 448. So keep in mind what kinds of answers you're expecting. Number 49. Once again, this is a geometric sequence explicit rule, as it's to that I minus 1 power. 10 terms. First term is 4. Common ratio is 3/4. Now, your sum should end up, as the numbers get smaller, you're still adding positive numbers, so the sum will still get bigger, just not significantly bigger. So your first term is 4. Common ratio is 3/4. And your number of terms, once again, is 10. So your series sum, you take the first term times 1 minus the common ratio to the 10th power over 1 minus the common ratio. This is, once again, one of those things that I like to do some cleanup, personally. 1 minus 3/4 is 1/4, and dividing by 1/4 is the same as multiplying by 4. 4 times 4 is 16. So there's a little bit of cleanup I'm going to do there, y'all. Just a little bit. There's no more denominator, and I'm going to do that in my calculator. 16 times 1 minus 3/4 to the 10th power. That 3/4 needs to be in parentheses, and if you're multiplying that result by 16, you need to do that as well, or you need to put this as 0.75. So like that. And there we have this number. Now this number looks a little weird, but it's a number that we're going to have to go off of if you don't write the fraction version. Will my calculator give me a fraction version? Not a chance. So this is one where we're just going to have to leave it as it is. There is an exact fraction version. And if we're curious to come up with it, then your calculator would have to help you on what 3/4 to the 10th power is in fraction form. And I don't think it's willing to do that. So if it's not, then let's not worry about the fraction. If it's not going to do it, then let's not worry about the fraction answer, because there is one. There is one. Now, for me personally, I would like exact fractions if I can get them, and they're not going to give it. So I would just write, honestly, I'd write as many decimals as I could. 15.09898376. And for all I know, that is exact. I don't know where the decimals stop for the exact fraction, but it is an exact fraction answer. There is, well, all of them have it. Just don't round if you don't have to. Here we kind of had to because the calculator wasn't helping us. Sorry that I felt like I was repeating myself over and over, but I need to state that clearly. By the way, that sum of those 10 terms was just 15. We're adding 4 with 3/4 of 4 is 3. 3/4 of 3 is whatever. You're adding smaller numbers and it's starting to converge. When we talk about infinite geometric series, we're going to see those values of convergence over time. All right, so I equals 1 to 8. That's 8 terms. Our first term is 5, and common ratio is 1/3. So for this one, eight. All right, so for this one here, we have a sum of our first 8 terms being our first term times 1 minus common ratio to the 8th power. That's a 1/3. Let me fix that a little bit. Over 1 minus common ratio. This is over 2/3. I mean, at some point you let your calculator take care of things, but you got to be careful here as well. Over 2/3, you also would have to put in parentheses, or you put 1 minus 1/3. I'd rather multiply by 3/2, but even then, if I do times, dividing by 2/3 is multiplying by 3/2, which makes this become 15 over 2. So I'm good with that, or 7.5. You can put 7.5. I'm good with that. And again, I'm expressing out loud how that comes to be, and I hope you're recognizing it when I say that. 7.5 may be a decimal, and I can still get a fraction answer if it allows me to. The only reason it might not is just because 1/3 to the 8th power can be a pretty big number. So let's check this out. 7.5 times 1 minus 1/3 to the 8th power. funky decimal fraction. This time they gave it to us, right? So there's the exact number that's as reduced as possible, and I'm going to go and use it. 16400 over 2187. Again, there are a lot of things that can go wrong with your calculator input, even when you have the exact formula right here. From here, you type this in wrong by missing parentheses here, or missing parentheses here, or missing parentheses where this would have said 2/3. You're going to get a wrong answer. That's why I like to reduce where I can, where I know where I can. Now, number 51 has something seemingly tricky to it. And I got to think about how I want to present it to you. Here's the thing. Not everything's always about the list of numbers as a geometric sequence from the first term onward. They have an I value of 0, which means we got to respect that 0, I equals 0 is a part of our list. That being said, your first term is always the lowest bound term from here. Might have also noticed this doesn't say I minus 1. It just says I. But that actually acknowledges, excuse me, that actually acknowledges why there's a 0 here. Our first term, a sub 1, we actually use a sub 0. We got to substitute the lowest bound in here. 8 times negative 2/3 to the 0 power is 8 times 1, which is just 8. Your first term is still 8. It's still that number in front, but for a completely different reason. Okay. This is some stuff we spoke about in, I guess not here. I don't know. Common ratio is negative 2/3, though. That's still the number that's being raised to the exponent, therefore that's common ratio. Now, n's tricky. It's actually not 8. It's actually 9. From 0 to 8, there are 9 numbers if you count 0. See, from 1 to 8, there are 8 numbers. From 0 to 8, there are 9 numbers. So that's the tricky part about this. There are 9 terms. There are 9 terms. That's something we did speak about in the arithmetic sequence set. So the sum of the 9 terms, we take our first term, 8, not a sub 1, but a sub 0. We take our first term times 1 minus r to the 9th power over 1 minus r. Oh, just so much that can go wrong. You're thinking, look, I'm trying to think how much this stuff cleans up. It can clean up a little bit. I'm going to type this one in the calculator as it's supposed to be. See if you can follow me with it. I'm going to do 8 times 1 minus negative 2/3 to the 9th power divided by 1 minus negative 2/3. That's a lot of things to do with parentheses to not make a mistake, and I can see where a lot of people would, but this ends up being an answer. Exact fraction, they give it to us, so even as an exact fraction, we can get something there, and that should be the result. So S sub 9 equals, and that is 32312 over 6561. Now again, there's some cleanup to be had if you'd like to do that in between. My personal go-to would be to do that, as in 1 minus negative 2/3 is 1 plus 2/3, which is 5/3. And 8 divided by 5/3 is 8 times 3/5, which is 24/5, which is 4.8. So I can turn this into 4.8, while 4.8 multiplies with that whole thing, and you can still get the same answer. So there are things you can do with it. I'll leave it. But yeah, there are things you can do with it like that. Number 52. 52 is like 51. We have to the I power instead of the I minus 1 power, but as a replacement for that, we start from I equals 0 to I equals 9. Therefore, we have 10 terms, and your first term is that one that's fronting right here. It is 9. But your first term being a sub 0, which is fine. Common ratio is negative 3/4. There are 10 terms. From 0 to 9, 0 counts as one of them. There are 10 terms. So the sum of your 10 terms, you take your first term, multiply by 1 minus the common ratio, raised to the 10th power, over 1 minus the common ratio. Yeah, let's do the calculator thing, just like we did before. I'm running out of inventive ways to go about problems, personally. 9 times 1 minus negative 3/4 to the 10th power divided by... Now, listen, if you know minus and negative is adding, that's great. But I need to talk about one more thing with this as well before you accidentally do that when it doesn't apply. All right, there's an answer, and I don't get a good fraction version of it. So the answer that I'm going to write, 4.8. I'm going to write as exact as I can, y'all. It's probably approximated. Unless they ask you to round. And listen, a teacher's going to ask you to round at some point here. Maybe they say round to the nearest 2 decimal places or something like that. Or exact fraction, but I couldn't get you one. Now, here's where you got to be careful. 1 minus negative 3/4 is 1 plus 3/4, right? Now, I'm not talking about what that turns into, but just as far as we simplify, this can be a plus. Yeah? Can we turn this into plus? This was minus a negative as well. Can we turn this one into a plus? No. That's the tricky part. Here's the thing. PEMDAS. This has to go first. And a negative raised to an even number turns positive. This minus is still here. We would do 1 minus whatever that result is. It doesn't turn into a plus because that is an even number. So as much as you might do some simplification, yeah, this will become a plus. That doesn't. So you just got to be careful what goes where, and you just got to be careful. Listen, I'm warning you of it. I'm letting you know. That's where mistakes are made. So a lot of mistakes can be made in your calculation, even if you know the formula. Even if you're given the formula. Okay, in exercises 53 and 54, find the sum. The first 8 terms of the geometric sequence, negative 12, negative 48, negative 192, and negative 768. The goal here, again, is to use that formula for the first 8 terms. If I wrote out sigma notation, which is not a requirement, if I wrote out sigma notation, I'd be going from the first term to the 8th term, given the rule of the first term being negative 12. Common ratio is clearly 4 to the I minus 1 power like that. Great. That doesn't really help us. What we need to write out, though, are first term, common ratio, and number of terms. We use our formula, and we're good to go. So again, this was fun. Not a required part of the problem. So S sub 8, we have the first term times 1 minus the common ratio to the nth power over 1 minus the common ratio. I am going to do some simplification here, y'all. I'm actually going to, this is negative 12 over negative 3. In past years and such, I would be even writing out what 4 to the 8th is and stuff like that. If the number's too big, I'm just going to leave it. But negative 12 over negative 3 is positive 4. So I'm going to be doing 4 times 1 minus 4 to the 8th, okay? That's my calculator bit. Now I'm expecting a negative answer. You noticed all of our numbers were negative to begin with. And through this calculation, it looks like it'll become negative. We're getting, I guess that number's not too big, negative 262,140 is my go. There you are. Number 54, the first 9 terms of this sequence. Once again, everything is negative, so I expect a negative answer. This time I will not write the sigma notation. I don't think there's an actual application for us to it. 378. Okay, so for the first 9 terms, we know what n is. Here's your a sub 1, and your common ratio is 3. That's what we're multiplying by there. So S sub 9 is your first term times 1 minus your common ratio to the 9th power over 1 minus your common ratio. Let's clean some things up right now. 1 minus 3 is negative 2, and negative 14 divided by negative 2 is positive 7. So if you want to work some stuff up right now, that might be the cleaner way to do it. So I'm going to do 7 times 1 minus 3 to the 9th power, and I'm getting negative 137,774. That was just through the calculator. Should be negative. Okay, number 55 in writing says compare the... This is a lot. This is just like the arithmetic sequence stuff. This literally feels like a carbon copy of it, which is fine. It's just interesting. Compare these 2 graphs. It'll be the same kind of answer as I had for the arithmetic sequence one if you did the question on that one as well. The sequence graph I'm not going to speak on this too much. The sequence graph is discrete and has a domain of, you start from 1, the whole numbers, 1, 2, 3, etc., to infinity, whereas the function is continuous with an all real number domain. Otherwise, both graphs are exponential. Both graphs are the same exponential pattern. Now, I didn't write out what they were, so maybe I should do that. But the two that I'm talking about, the sequence graph is for this one. A sub n equals 5 times 3 to the n minus 1 power. That's the sequence graph. The other one is f of x equals 5 times 3 to the x minus 1 power. That's the function version right there. So one, you don't connect some dots and they start from n equals 1. This one, you connect all the dots and it goes forever. Left to right. Number 56, abstract reasoning. Use the rule for the sum of a finite geometric series to write each polynomial as a rational expression. So A is 1 plus x squared plus x cubed plus x to the fourth. I guess they're saying that if you use that rule, then it'll have a division part in it, and that can help you out. If you notice for this sum, a couple things. First of all, your first term. Second of all, your common ratio. We're multiplying by x each time. There's another x going on. And the number of terms, there are 5 of them. So let's write it out with this in mind. This is kind of fun. S sub 5, that's an S, that's a 5. S sub 5 equals A sub 1 times 1 minus x to the n, or common ratio to the n power, over 1 minus common ratio. So this can be also written as 1 times that is just that. So 1 minus x to the fifth over 1 minus x. This is n answer. I kind of would prefer to factor out negative ones on each of these. So this is fine. I'd prefer to do, I don't even want to write the s sub 5 part. I'd rather factor out negatives from both of these. So this is x to the 5 minus 1 and factor negative out here. And that's x minus 1. Negative over negative is positive. So I'd rather write it like this personally. Which this is the factorization of it. And if you know some stuff from, well, you might not know this one. But this is factorable. And obviously it leads to this. You know what? I guess that wasn't in standard form to begin with. So maybe that's why they should write it this way. Anyway, that's the answer to A. B. We have 3x. Oh, these increase as well. Plus 6x cubed plus 12x to the fifth plus 24x to the seventh. We still have to find that common ratio. We have a first term of 3x. Common ratio looks like 2x squared, I think. 3 times 2 times 2 times 2. X times x squared times x squared. Yes, 2x squared. And there are 4 terms. These are kind of interesting problems. So the sum of the first 4 terms, we start with the first term. It's 1 minus r, you put it in parentheses, to the nth power all over 1 minus r. I'll leave this as is. It's not even a difference of 2 squares or nothing like that. And it seems like they would have been fine doing this, how it's written. So let's clean it up a little bit. And this is 3x times 1 minus 2x squared gets raised to the 4th power. 2 to the 4th power is 16. X squared to the 4th. You don't do 2 to the 4th. You do 2 times 4 and you get 8. So this will equal, if I distribute the 3x, which I feel like doing, that's 3x minus 48x to the 9th over 1 minus 2x squared. They said write them as rational functions, and that's exactly what this thing is. Good old rational. I could factor out negatives again. I feel like they probably weren't necessarily digging that. This looks fine for this answer as well, by the way. All right, kind of cool question. Nothing like the arithmetic things we had before. Number 57 and 58 says use a monthly payment formula given in example 6. Okay, for me to do that, I have to remember what it was. I don't exactly. I have ideas of it. Hold on, let me try it. It was L. I don't remember what was on the other side. It was L, which was the loan, over the sum of, don't worry, I'm going to go find it in a second. From 1 to T, I guess T is always in months. So if they say monthly payment, we always have to do monthly payment of 1 over 1 plus I. Oh, what happened here? I have... I don't remember what this was. Hold on, let me find it. Okay, I found it. I was really close. I was thinking there's a K. Where's the K? It's right there. So to the K power. So I was really, really close. So this part's to the K power like that. Oh, it's K equals 1, I guess. The I is the interest rate. K is the variable that's used in that sense there. All right, well, I was close. And this, this is M for monthly interest rate. Awesome. Okay. Anyway, I'm going to cover mine with theirs. So there we have it. Okay. 57. You are buying a new car. You take out a 5-year loan. Now, time is in months, is monthly payments. So 5 times 12 is 60 months. 5-year loan is 60 months. For $15,000, that is your loan amount, $15,000. The annual interest rate of the loan is 4%. I itself is 4%, but because, we'll read it in decimal form, because it's monthly, we divide this by 12. Is that a repeated decimal? That's not going to be any fun. I'm just going to write it as 0.04 over 12 for now. Because that would be a repeated decimal. Calculate the monthly payment. Okay, so given that, we're going to say, I'm trying to see where I have room. Okay, the monthly payment is $15,000 over the sum from K equals 1 to 60 of 1 over 1 plus 0.04 to the 12th power for K, to the K power. Now, the bottom is this sum formula. You have to keep in mind what this thing's all about. If K equals 1, right, the first term, it's all about the first, we're doing a sum formula still for the bottom. So for this bottom portion, right here, our S sub 60, we need our first term by substituting 1 in here, and that's this. And I'm not going to simplify that at all unless that would clean up, and I don't think it does. Maybe it does. Let me try it. 1 over 1 plus 0.04. It's 300 over 301, so it does clean up, at least for this term. So there's for one term. Oh, if that cleans up like that, then this is always 300 over 301. So let me actually even just write that here now that we plugged it in. And I hope that's okay. So 300 over 301. Now that's also your common ratio because that's the thing that's raised that power. So it's both your A sub 1 and it's your R, which is interesting enough. And this is one where I'm probably not going to do too much cleanup here and there. I could do some of it actually. And N is 60. Your number of terms is 60. So when it comes to your formula, this is just the bottom portion. So S sub 60, hopefully I don't have to do this too many times. S sub 60 is A sub 1 times 1 minus R to the nth power all over 1 minus R. Now, there is some good cleanup to be had here given all the stuff we have with these numbers. This part won't get any better. You could type the stuff in, but 1 minus this is just 1 over 301, which means you multiply both sides by 301, which means these 301s go away. You're left with just the 300 up here. If my math is mathing on that, that's all that would be. So S sub 60, I'm just going to take 300 times this thing here. So I'm going to go to the calculator for that one, and let's do 300. I'm saving myself some information to write. 1 minus 300 over 301 raised to the 60th power. So this is something weird. Now I'm going to leave that number as is, in that now what we have to do is divide 15,000 by that number, which was 54 or something. Okay, so let's do that. Let's go to 15,000 divided by that previous answer. And that gets you your monthly payment of $276 and about 25 cents. So what I have to do, I'm just going to say it like this, M, because I don't want to write out decimals that are early rounding. That's why I want to use exact answers. M is 15,000 over, well, we had the computation. It's just that number. It's around $276.25 of a monthly payment. So there's a lot to be done there, and I'm sure there's a way in the calculator to make that sum part go faster, but that's essentially it. All right, number 58. You are buying a new house. You take out a 30-year mortgage for $200,000. The annual interest rate of the loan is 4.5%. Calculate the monthly payment. I don't know why I stressed annual. It's still a monthly payment. All right, so number 58, I don't think there's really any change for this stuff. T is 30 years times 12 months is 360 months. Something that sounds like a lot of months. $200,000. Yeah, I've never done questions like this before. $200,000 mortgage, a loan, and your interest rate is 4.5%, 0.045 over 12. I don't know if that simplifies. Like even just as a decimal, if it's non-repeating. Yeah, it's non-repeating. This one's 0.00375. So at least I can write a cleaner version of it. And I'll tell you what, the even the book uses this storage variable thing, and I'll show you how that one works for this problem as well. So we're going to do 200,000 divided by the sum from, month 1 to month 360. This is 1 over 1 plus this. So 1.00375 raised to the k power. Your A sub 1 and your R are both the same thing as they were last time. Now, does one, this is where the calculator, this is where the book used the calculator in such a way that when it did 1 divided by this, look, this number itself don't pan out to be very pretty, even as a fraction. I mean, it's a fraction number, it works out, but let's just store it as some variable. I think they use the letter R. Why don't I just use the same thing? Is that R? We'll just store it as R there. Great. That's both your A sub 1 and that's your common ratio. Your A sub 1 and your common ratio are the same thing in these particular problems. So A sub 1 equals R. Common ratio is R. These are storage variables in the calculator. Please understand what I'm doing with those. It's this number here. R is that value. And then N is 360. So when I do this in the calculator even, literally, I get to do this. S sub 360 is going to be A sub 1 times 1 minus R to the N power over 1 minus R. This time, I'm going to let the calculator do it, but make sure you put parentheses around your denominator. So I'm going to do R, that's M. I'm going to do R times 1 minus R to the N power all over, in parentheses, 1 minus R. This isn't the answer. Whoops. This isn't the answer. That's M again. This is the denominator. So that's my S sub 360 value, okay? And now we get to do 200,000 divided by that value. It's the same thing as last time. We're doing 200,000 divided by that sum of those terms, kind of trusting what the calculator is doing with it. And then this is our monthly, mortgage payment? The monthly payment for the house. So we are going to say, well, M is, 2,000 over that thing. So it's about, what was it? $1,013.37 per month. And there's the calculation. So a lot to be had on those. It's a lot. It's a lot. That's what I'm here for. Number 59. A regional soccer tournament has 64 participating teams. It looks like all these problems are being big at the end. In the first round of the tournament, 32 games are played. 64 teams, 32 games, right? Two teams per game. In each successive round, the number of games decreases by a factor of 1/2. They're talking about number of games played, not number of teams that there are. So 32 games in the first round, and it's cut by 1/2. 16 games in the second round, and then 8, and then 4, and then 2, and then 1 game for the championship, I assume. So probably 6 terms. Write a rule for the number of games played in the nth round. For what values of n does the rule make sense? Explain. Given that I just wrote out the list, it only makes sense until you only have 1 game left. in terms of integer amount. You can't have a fraction of a game, and there probably shouldn't be 2 games when it comes to the tournament. So when it comes to this rule, they said write a rule. So part A, first term is 32, common ratio is 1/2 n minus 1 power. This works for n values. For what values of n does the rule make sense? This works for values of 1, 2, 3, 4, 5, 6. Because at some point can only have integer number of games. Can only have integer number of games down to 1 game. Does that make sense? Part B, find the total number of games played in the regional soccer tournament. Clearly we can add these up if we were going off our rule. First term is 32. And you would work it out this way. And I'll tell you what, I'm going to do this without a calculator. It's ambitious, right? 1 minus 1/2 is 1/2. 32 divided by 1/2 is 32 times 2, which is 64. I get to do 64 times this, and 1 minus 1/2 to the 6th power is 1 minus 1 over 64, which means this gets to be 64 times 63 over 64, which means it's 63. 63 games played. I'm going to double check that. 32 plus 16 is 48, plus 8 is 56, plus 4 is 60, plus 2 is 62, plus 1 is 63. Yes, 63 games. You don't need a calculator. Of course, you could have just added these together to start with. Okay, number 60. Modeling with mathematics. In a skydiving formation with R rings, each ring after the first ring has twice as many... Oh, those are skydivers. I know I read skydivers, but I was like, I thought these were like fractals. Those are people. They're like holding like, ah! It's the barrel of monkeys from IM3. Or it's skydivers. So each ring after the first has twice as many skydivers as the preceding ring. So I have a ring, if I'm looking at this here, I have a ring of... You can't see that. I have a ring of 1, 2, 3, 4, 5 skydivers, and when you attach them, the next would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This tracks. Okay. The formation for R equals 2 is shown. Yeah, here's ring 1, and here's ring 2. Let A sub n be the number of skydivers in the nth ring. Write a rule for A sub n. So we do have an A sub 1 of 5 and a common ratio of 2. So our rule for part A can be A sub n is 5 times 2 to the n minus 1 power. Remember, this is not for the total number of skydivers. This is how many skydivers are in that next ring. They say find the total number of skydivers when there are 4 rings. Now, the practical approach, of course, would be 5 plus 10 plus 20 plus 40, which would be 75, 75 skydivers. And if you want to go about it that way, that is the easiest way. I'm not stopping you. No one should be. If you want to look at that formula and that rule, you would take the first term times 1 minus r to the fourth to the nth power over 1 minus r. 1 minus r. 1 minus 2 is negative 1, and 5 times divided by negative 1 is negative 5. So you'd have negative 5 times 1 minus 16, which is negative 5 times negative 15, which is 75. No calculator. No capes. Okay, 6 more questions, though they all look big. I don't even know what to do here, guys. Wait, is it 6 more? Yeah, I think so. All right, number 61. Oops. The Sierpinski carpet is a fractal created using squares. The process involves removing smaller squares from larger squares. First, divide a large square into 9 congruent squares, then remove the center square. Repeat these steps for each smaller square. So now the smaller square, remove the center square, Repeat these steps for each smaller square as shown. That's really cool. Assume that each side of the initial square is 1 unit long. What is this? Wait, is this the initial square here? Or they're talking about this? I think they mean this initial square here. So this is 1 unit. That means these are a third of them. Yada, yada. Let A sub n be the total number of squares removed at the nth stage. So stage 1, we have 1 removed. Stage 2, we have 9. I can only imagine at stage 3, we have 81. If you count that out, 1, 2, 3, 4, 5, 6, 7, 8, 9, and that also has 9 here, 9 rows, 9 columns, it's 81, etc. So this is for stages 1, 2, and 3. We have that many removed. Write a rule for a sub n. We have a first term of 1, a common ratio of 9. So this would be our rule here. Remember, I don't need to write the 1. If it's just going to multiply by something, it just remains as that. So that can be our part A. It says, then find the total number of squares removed through stage 8. Remember that total number of squares removed at the nth stage. Oh, hold on a second. Is that also this? I need to think about this because that's how many squares are removed in those things in total. So let me do that again. This sequence should not be 1, 9, and 81. That should be the sum. Here, there were 8 squares removed at the stage. So I need to write 8 here. In these ones here, there are 8 in this one, 8 in this one, 8 in this one, and there are 8 total. That makes 64. So I actually need to do it like this. I need to do it like that. So now the rule is going to be a sub n equals common ratio of 8 to the n minus 1 power instead of 9. 9 is the total number in each set as an overall. We're going to probably use a sum formula for that one, of course. Then find the total number of squares removed through stage 8. That is going to be the sum of those through n equals 8. So we need to get the first term of 1 times the common ratio, 1 minus r to the nth power, they're both the same thing, over 1 minus r. I'm going to go straight calculator mode on this one, to be honest. So 1 minus 8 to the 8th power divided by negative 7. I'll at least give me that. And that is 2,396,745. That's 2,396,745 squares removed in stage 8. Just stage 8 alone. No, through the first 8 stages. That's the sum. Now part B says let B sub n be the remaining area of the original square after the nth stage. Write a rule for B sub n. Then find the remaining area of the original square after stage 12. So for this one here, well, 1, the original square is 1 unit long. That means its area of this original square is 1 by 1, which is 1. And we are subtracting areas out of whatever is there. So B sub n should be 1 minus, I believe, A sub n at any n value. So, wait, does that sound right? Well, this was the number of squares removed. I take it back. A sub n isn't about area. A sub n is about the number of squares removed. So if we are subtracting, let me think about this. We're subtracting areas that add onto each other. B sub n be the remaining area of the original. Oh, here's the thing. You have 8/9 of what remains. If there are kind of 9 squares cut out into this stage there, you have 8/9 of remaining squares. So instead of subtracting from 1, you kind of would, but you remove a square. So that's 8/9 to the n minus 1 power. I need to make sure that's right. Let me think about this. After the nth stage, the remaining area of the original square after the nth stage. So if I remove, I don't know if it's n minus 1. Stage 1 should have 8/9 remaining. So it should just be to the nth power. Now, if I did stage 2 to the 2nd power, notice how 1, 2, 3, 4, 5, 6, 7, 8 need to be added with that. 8/9 8/9 of 1/9 is 8 over 81, and 8 over 81 plus 1. Sorry, I need to see this. I need to see if this works. You have a syntax error. I must have typed something wrong. It says after the nth stage. That's the only thing that I'm looking into. 8/9 squared. That's a different number. Oh, how much area is remaining? Oh, I think that does work. Sorry, I'm testing. Yes, okay. Things I'm testing in the calculator right now. I was trying to see what happens. 1/9 is how much is removed after the first square. 8/81 is how much is removed in the second in stage 2, because there are 8 of these ones. This is 1/81, 1/81. There are 8 of them plus the 1/9, and that becomes this area right here. I might be overthinking the problem, which is not something I endorse. So that becomes this here. This is how much is removed in area. 8/9 squared is if I substitute 2 for stage 2 for this, and this is how much area remains. And 1 minus what I remove is what remains. 1 minus what remains is what's removed. So those do match up. Okay, so I trust what I put is correct for a b sub n. Says then find the remaining area of the original square after stage 12. Now we just substitute 12 into here. It's not a sum because this accounts for the sum. So 8/9 to the 12th power. Let me do that. And that's around 0.24. I don't know how much I'm going to write. I'm going to round to 3 decimal places. Around 0.243. I don't know the units. 1 unit long, so square units. This is how much remains there. Okay. I lived on that problem for a little bit. My bad. Number 62, how do you see it? Match each sequence with its graph. Explain your reasoning. Straight up, it's all about common ratio. If a common ratio is more than 1, your numbers are going to increase. If it, exponential growth. If it's less than 1, it's going to be decay. And that's what we're experiencing here. So, A, graph B, because r is 1/2, will show exponential decay. And then for part B is graph A, because r of 2 will show exponential growth. All right, that's it. All right, number 63, critical thinking. On January 1st, you deposit $2,000 in a retirement account that pays 5% annual interest. You make this deposit each January 1st for the next 30 years. How much money do you have in your account immediately after you make your last deposit? Let's make sure we process how that needs to calculate. But January 1st, you deposit $2,000 in a retirement account. I assume this is kind of like your A sub 1. So $2,000 that deposits 5%. I'm using R in a different way right now. That R is not just common ratio. R is the interest rate. So let's do 1 plus this. 5% annual interest is 1.05. You make this deposit each January 1st for the next 30 years. What I have to be careful of is whether this means it's done 31 times. 2,000 is the initial. So I think all I get to do here is, and I don't know how to write this this other part here for y equals A sub, I'm just going to do A sub n. A sub n is 2,000. I believe we're just going to do 1.05 to the nth power. That way, when n is 0, we still have the $2,000 deposit. But each January 1st for the next 30 years means on the first year of the next deposit, we should get that 5% increase. So I should be using this. So we do, how much money do you have in your account immediately after you make your last deposit? We should just be substituting 30 into here. So 1.05 to the 30th power. That's my belief. I'll think twice about it. I'll go over it again in my head and make sure that that kind of makes sense to me. Oh. You know what we have to do, actually? Let me think about this. We are depositing $2,000 regardless. But those amounts of money are adding... Okay, so here's how it works. I don't want to just do this. This actually... Here's... This is fine. This just isn't the answer. This represents how much money is made from my first deposit. I deposited $2,000, and 30 years later, that $2,000 has become this amount of money. And I calculated, and I was thinking I should get a big answer. This was around $8,000 something dollars. That's for that one deposit. Now, the next year I did another $2,000 deposit, and that gains interest for 29 years after. The next one does it for 28 years. So what we have to do is find a sum. So don't worry about this one. What we have to do is find the sum. Here's our first term. Here's this, and n is 30. That's all great. So we have to find the sum of these 30 years of deposits, where basically the first term is really our last deposits amount. But that's okay. We still add them up together. So this is 1 minus r. Oh, now does r get to be 1.05 or 0.05? I think it's still 1.05. 1.05 to the 30th power over 1 minus 1.05. Let me I'm going to pause and compute this, kind of see how things pan out, if it feels right when it comes to big numbers, stuff like that, and then I'll come back to you. Okay, I'm back. Number seems fair. So when I'm calculating this, it looks like I'm getting a bigger number out from it, which is something that I expected. So I'm going to go ahead and use that one. So after my last deposit from the 30-year bit, we're getting a total, when we add in all our deposits, of $132,877 and about 70 cents. So sorry, I'm writing it. 70 cents. Yeah, if I just did it straight up, if I did $2,000 a year for 30 years, that would be about $60,000. So that interest really helps build up. You get more than double your money from that, which is cool. Okay, number 64, thought-provoking. The first 4 iterations of the fractal called the Koch snowflake are shown below. Koch. Find the perimeter and area of each iteration. Do the perimeters and areas form geometric sequences? Explain your reasoning. All right, the triangle is going to be easy. After that, I'm going to have some pause. Let me copy and paste this so I can write right underneath them. Area? Hopefully I can pick up the pattern really easily and not have to deal much more beyond that. It's probably one of the things I should pause for. Perimeter here is 3. Area is actually a little bit trickier. 1/2 base times height. The height of this thing, I mean, there are different ways you can do a formula for it, but in 30, 60, 90 triangle, this is 0.5 and 0.5 root 3. 1/2 root 3? So area is 1/2 base. Oh, well, you could do 1/2 apothem times perimeter. 1/2 base times height, which is root 3 over 4. So, okay, there's that one. I have to think about how all the other areas will work. Here's the thing. These are divided into smaller triangles, so I just need to figure out the size of these triangles in comparison to the originals. I think I'm going to feel better about it when I get there. Now, the thing we can recognize is this triangle is still here. So this triangle that shows up is just an upside-down version of it. So I guess the area isn't necessarily doubled, but we can find out how these things are cut off. These ones are divided into thirds, basically. So now this is 1/3, I imagine. That's how that's working out. So the 1/3s go around the outside, round the outside, round the outside. And we have, are we doubling? No. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12/3 is 4. So this perimeter is 4 instead of 3. Well, hopefully after 3 of them, we'll recognize what the full pattern is. So I don't really have to count the last one and figure out what's going on. Let me actually start with perimeters. I'll do areas after that. These perimeters must be divided into thirds as well, right? Because now this triangle has the thirds going on. So these are ninths. So let's just kind of count this out. For this set here, we got 1, 2, 3, 4, 5, 6, 7, 8. So that's 8 ninths. And there are 1, 2, 3, 4, 5, 6 of them. Is that 48 ninths? 48 ninths to 16 thirds. So that'd be my perimeter for that one. Does anyone see a pattern there? From 3 to 4 to 16 thirds? It's clearly not arithmetic. So for perimeter, 3, 4, 16 thirds. Are we multiplying by 4 thirds each time? 4 divided by 3 is 4 thirds. 4 over 1 times 4 over 3 is 16 thirds. Yes, it is. So I'm going to guess that the perimeter of the last one is 64 ninths. Therefore, this is geometric. I'm not going to land on that last one as a whole. I'm just going to go ahead and leave it like that. The area of this one was root 3 over 4. Now, I got to think about a way that we can get the area in this next one in a calming way. If I take the original area of this one, which is root 3 over 4, let's just try and get the other one by adding these 3 individual parts, which is, hold on a second. There's an inner hexagon. That triangle, that triangle. Sorry, my process sucks. I think all these have these individual triangles within, so there are a bunch of small triangles like that. That means this one big triangle is divided into 1, 2, 3, 4, 5, 6, 7, 8, 9 smaller triangles. That means this is a third of those smaller triangles. That means we can do root 3 over 4 plus root 3 over a third of that, root 3 over 12, plus root 3 over 12. Multiply that by 3 over 3. That is 4 root 3 over 12, which is root 3 over 3. So the area of this one is going to be root 3 over 3. I apologize if I did not show you too much on how that one works. I reckon whoever I'm speaking to on these problems can do exactly what I just did on their own. And I'm just coming with pattern things on it because I have to think about these. So when root 3 over 4 to root 3 over 3. Does that mean the next one's root 3 over 2? No, that's not necessarily how denominators work when it comes to sequences. But how am I going to use that process to break this one down even more? I have no idea, guys. How about this? Do you think it's a geometric sequence? I don't know. I don't think so. That'd be a tough geometric sequence to play with. Let me, I kind of want to pause so I can track and say how I'm getting this next area. So, 'cause I don't want to spend a long time just looking at this area thing. This is a lot to take in. There must be a faster way for me to do it that I'm not recognizing. So let's see. Those triangles break into... This is harder to see how these triangles break up after that. How about this? I do notice this at the very least, where I have this upside down triangle kind of being represented there. The right side up triangle being represented here. Right? Those were the two OGs. We're only adding more area after those two. So how many of these are being added in, and what fraction of those triangles are they? So there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 of those. 12 of those, and they are... Were they 1/9? These were... I think 12 of those, and they're 1/9 the size of the ones that were 1/9 the size of the other ones. Is that right? 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is 1, 2, 3, 4, 2, 3, 4, 5. Oh, 1, 2, 3, 4, 5, 6, 7, 8. So I can take this and add 12 of these that are 1/9. Oh shoot, 1 over 81, the size of the original root 3 over 4. So is that root 3 over 324? Ooh, I might have lost where I am with this. Hold on, let me think about it. Okay, I think that tracks, because these are 1/9 the size of those that were 1/9 the size of the big ones there. So 12 over 324, if they divide by 324 divides by 12, you get 27. So this is root 3 over 3 plus root 3 over 27. Multiply this by 9 over 9, and you get 10 root 3 over 27. So this guy has an area, let me erase all that, of 10 root 3 over 27. Okay. The question is, does area have a geometric sequence? Root 3 over 4, root 3 over 3, and 10 root 3 over 27. I see no such inkling of it. I know there can be fraction reduction within. I'm still not sensing it. If I multiply that by 3 over 3, I get 1, 3, 10. I don't know how that works. 4, 9, 27. I don't know how that works. I don't think that's a geometric sequence. I could test common ratios, but that doesn't track. So not geometric. What was the question? Do the perimeters and areas form geometric sequences? Explain your reasoning. No, and I don't think I want to bother myself with the fourth fractal thing. I'll just say not geometric. Once I see 3 of them, then I can determine whether any of those have a common ratio and they don't. These guys have a common ratio of 4/3. This one, no common ratio. All right, there was a lot to do on that problem, and I kind of left it in the dust. Moving on from that one. All right, number 65. Making an argument. You and your friend are comparing 2 loan options for a $165,000 house. Loan 1 is a 15-year loan with an annual interest rate of 3%. Loan 2 is a 30-year loan with an annual interest rate of 4%. Your friend claims the total amount repaid over the loan will be less for loan 2. Is your friend correct? Justify your answer. Myself and finances are not compatible. I may teach math. I don't teach finances. So if I look at this stuff, I go, brother-in-law, can you help me here? Now we have a formula for this, though, right? We can look at monthly payments and multiply by the number of months to get the total loan and compare them, I guess. So if your loan, is $165,000 the loan? Yeah, 2 loan options. So if your loan is $165,000, we have 2 different sets. There is a 15-year loan, so loan 1. 15-year loan, the monthly payments 15 times 12 is 180. So 180 months. Interest rate for I sub 1 is 3%. That's a quarter. That's 1 over 400. 0.00. How many 2 5s are there? 0.0025. I gotta use a calculator. Yeah, 0.0025. All right, there's that. So the monthly rate, there's a lot to do for this problem because we have to do it twice. 165,000 over the sum from k equals 1. I'm trying to see if I remember this. K equals 1 to 180 of 1 over 1 plus I raised to the k power. So let's talk about this bottom part. Work that sum out. S sub 180 is, now let's see if that 1 over 1.0025 gets a cleaner number for us. As a fraction, it's 400 over 401. I think I want to do one of those things like I did previously on these and just write the fraction, store it into R. Store it into R like that. So let's just do that as we did last time. Last time I stored it into R, okay? So your A sub 1 is the same as your common ratio. We've seen this a couple times to note that. So 1 minus R to the nth power all over 1 minus R. This is S sub 180 for the first set, and that's just for the bottom sum. Then we got to we have a lot to do here. So R times 1 minus, oh, you can't see my calculator. R times 1 minus R to the 180. I hope I'm doing this right. Over 1 minus R. This has really slowed me down. Okay, I'm going to do all this like really like fast. So there's something, a sum of something. We divide 165,000 by that number, and this becomes the monthly payment. If you multiply that by the number of months, that should be the total payment on the loan. That's 180 months. So I'm doing a lot there, like the on paper stuff, like in the calculator. So that's $205,102.75 repayment. See, I don't know the verbiage. I'm really bad at that. So I'll say that 180 times this. I would say about 205,000. I doubt the other one is going to be really close to it, or it's going to be significantly different, so we can tell. So let's just use that as that answer. Now the second one, sorry, I'm working slowly through this, trying to process if this is how this stuff works. The second one is a 30-year loan. So 30-year loan, that's 360 months. 4% interest rate. This will not simplify. This will have a repeated decimal, so I can't say too much on that. So I'm definitely going to be using the calculator on that next portion. We're going to do 360 times m at some point. So we'll do 360 times the 165,000. Listen, I'm going to do 165,000 first just to talk about the monthly. But this is from 1 to 360 of 1 over 1 plus 0.04 over 12 raised to the k power. Your a value is going to be that r and such, so let's go to the calculator. Let's use 1 over 1 plus 0.04 over 12, and we're going to store this value as r. There is a fraction equivalent, 300 over 301. I think we've seen that before. But we're going to store this as that new r. Okay, let's do the same thing as before with this stuff, okay? We're going to do our a sub 1 times 1 minus r, and it's the same thing, r's common ratio, raised to the 360th power over 1 minus r. I feel like there's a fast way for me to do this, and there might not be. So there's this number here. We're going to divide 165,000 by this number to get the monthly of this. And then we're going to multiply, so there's the monthly, and then we're going to multiply that by 360. This is the total. So the total there, I don't know, around 280,000, 285,000, something like that. 284,000, I'll just say. So this is around 284,000 there. So we compare the two, one's bigger than the other. The question is, which one would you want? I actually don't know. Your friend claims the total amount repaid over the loan will be less for loan 2. They're wrong. The amount paid is more for loan 2. So my friend is incorrect, as per usual. My friend is incorrect. You pay more for loan 2. All right. That's where the finance guys come in. Okay. I'm done with that. Number 66, last question. Critical thinking. Let L be the amount of a loan in dollars. I be the monthly. Okay, well, we've seen a lot of that. And M be the monthly payment in dollars. Part A. When making monthly payments, you are paying the loan amount plus the interest the loan gathers for each month. I might struggle. For a 1-month loan, T equals 1. The equation for repayment is L times 1 plus I minus M equals 0. I'm freaking out. For a 2-month loan, I'm so close to the finish line. For a 2-month loan, the equation is L times 1 plus I minus M times 1 plus I minus M equals 0. Solve both of these repayment equations for L. Okay, well, I'm just getting L by itself on these. That's not too hard. All right, so for the first one, here, I'm going to add M to both sides. And here I get, divide both sides by 1 plus I, and I get m over 1 plus I. All right. So there's that one. On the other one, we have the equation that says L times 1 plus I minus m times this 1 plus I, and then minus this m equals 0. First, we'll add m to both sides. Then we'll divide both sides by 1 plus I. This is probably the basis for how the formula works. I don't know. It's probably the basis for its existence. M over 1 plus I. Now if I add this m over, I'm just going to do it right now, plus m here, and then we divide by this one. Listen, I'm going to do this kind of fast because I keep rewriting the same stuff. Divide by 1 plus I. This inherits a 1 plus I, and this inherits another factor of the 1 plus I. So this is going to be L equals, I kind of feel like the second one is supposed to be written after. So m over 1 plus I plus m over 1 plus I quantity squared. Kind of like that. So you can recognize potentially a pattern here. This is why I wanted to bring this up. This one's written first. I said I feel like this should be written second just to show that. Okay. Part B. Use the pattern in the equations you solved in Part A to write a repayment for a T-month loan. So for a T-month loan, remember, you're taking the sums of all these things. It's not just the last ones to the T power, but sort of. So for Part B, we could say L, I don't know if it's L sub T or whatever, but you take all this stuff, this plus this to the second power plus, because this was a 2-month loan, right? This was. So for T months, this would be 1 plus I to the T power there, but it's the sum of all of them. They said, hint, L is equal to m times the geometric series. M. Oh, yeah, m's on, oh, that's right, m can factor out. Okay, so this is L equals m times, yes, the geometric series. Your first term is this, and that's important because the common ratio is the same thing. 1 plus I squared plus 1 over 1 plus I to the T power. So, okay, your A sub 1 in this case is 1 over 1 plus I. Your common ratio is 1 over 1 plus I. I'm sure we can just write it as a sum. Well, we don't need to use the sum formula. I think, oh, excuse me, we can use sigma notation. What did they say? Write a repayment equation. I guess we can just use sigma notation. So we can say L is m times, and the sum takes, well, I guess we don't need parentheses. We can use times sigma notation, boom, 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 the summation for up to T. What did they use? K? From K, I can't use I because I have it already in the equation. K equals 1 to T of 1 over 1 plus I to the K power. Hey, this looks like a formula from before. Sort of. It kind of looks like the formula from before, right? Now they said, then solve the equation for M. Oh, yeah, when we divide, oh. Yeah, that is the formula. When you divide both sides by this thing. Okay, so M equals L over, oh. Well, now I remember how to do the formula. Not really, because the problem is I don't know how to do the first part. The first part gives you, so there's the answer. The first part gives you this thing. I don't know how to do that, but I trust the first part for me to build that up. All right. Part C, use the rule for the sum of a finite geometric series to show the formula in Part B is equivalent to that. It's equivalent to that. Use this formula to check your answers in exercises 57 and 58. So, this is more generic, I suppose. So we can use what we were doing previously, but in a generic sense. The sum... All right, so it just goes to show that the top on L here is still an L that's just factored out. So what we need to focus on is just that bottom sum itself. So let me copy, and I'm just going to do this on the next page because I want some binder paper lines. So let me copy paste this over here for a part C. Oh, that didn't copy. Let me copy paste this over here for a part C. This is the last question. Copy. Thank you. So for part C, we could also write this as m equals, notice how the L is factored out in their set, and we do 1 over this guy. So the sum, whoopsie, the sum from k equals 1 to this, and this is more generic because we have an I in the picture here and a T. So let's play with this bottom portion. So that sum of the first T terms takes the first term, which will be 1 over 1 plus I, and it multiplies by 1 minus the common ratio, which is 1 over 1 plus I raised to the T power, that's n, over 1 minus 1 over 1 plus I. Oh, geez. I don't think I've seen problems this ambitious before from this set. I apologize to anyone who has to do it and who has to watch me struggle through it. Now, 1 minus 1 over 1 plus I is the first thing I want to clean up. We've done a lot of those before, so we can multiply top and bottom by 1 plus I over 1 plus I like that. And subtracting the 1s, you just get I left. So this becomes I over 1 plus I. And I bring that up because 1 over 1 plus I over 1 plus I just becomes 1 over I. Which means I can write that as S of t equals, well, the 1 doesn't even need to be there. I can just divide this all by I. So here I have 1 minus 1 over 1 plus I to the t power. Now this is in the denominator. I don't know how to simplify that more. So this is in the denominator. Well, you could call this 1 to the t. Well, I take it back. Well, I don't know how their formula looks. Theirs doesn't have t. Oh, it has a negative t. I could do 1 minus 1 to the t over 1 plus I to the t. I'm sorry, that is a t that's right there. Over I. 1 to the t is just 1, so it's 1 minus 1 over 1 plus I to the t power over I. This can be, you know what? They have that as 1. Instead of getting a common denominator, let's turn that as 1 plus I to the negative t. Because that was 1 over 1 plus I to the t, right? That t doesn't really need to be there. So let's just do that. So now we have, so this is this portion of the denominator for this rule here. So now we have m equals L times 1 over this guy, this fraction, 1 minus 1 plus I to the negative t all over I. And 1 over something means we can flip that fraction in there. So this would become L times I over 1 minus 1 plus I to the negative t. Is that the same thing as this? Got it. All right. I showed that. That took a while. Use this formula to check your answers in exercises 57 and 58. Oh, okay. So for this one here, we need the monthly payments. So for the 57 revisited on this, we have an L of 15,000. T is 5 times 12, which is 60 months. I is 0.04 over 12. Again, something you can't kind of change there. So we're going to say M equals 15,000 times 0.04 over 12 divided by 1 minus 1 plus 0.04 over 12 raised to the negative 60th power. So let's use this calculation, or let's use our calculator and calculate those things and see what comes up. So we're going to get 15,000 times 0.04 over 12 divided by 1 minus, parentheses, 1 plus, there's a lot of parentheses, guys. Make sure you know when to put them and when not to. Raised to the negative 60th. I don't even have to close parentheses on that. I should just get a number. Boom. I seem to remember that number. $276.25. Which one do I like more? I might like that one more as an overall because I don't have to use the summation part. That's still quite a bit to do on that one. I don't remember the formula. And then the other one, number 58 on that. Remember, these aren't actual 50. This is revisiting 57 and 58 for the question. Number 58, you are buying a new house. So let's see. $200,000 mortgage. This is 360 months, 30 times 12, and 4.5%. I seem to remember that having a better decimal. Was it 0.024? 0.045 over 12. No, 0.00375. That helps for when I do some of the calculations with after. So the formula we're using, I'm going to go back to the page because they have it written on there. So last part. So this is M equals 200,000 times, oh, this is an R, this is I. I 00375 over 1 minus, and then 1.00375 raised to the negative 3/60th power. Like that. Okay. 200,000 times 0.00375 divided by 1 minus 1.00375 raised to the negative 360. I think that, no, I don't really remember that number as much, but I think that was it. So let's see. 1,000, I slightly remember it. 37. So I'm getting this answer here. Let's see if it compares to our number 58 from before. Oh yeah, it does. All right, guys. I couldn't be happier to be finished with something there. Y'all, that'll do it for this one. Thank you so much for watching. Coming up next would be the 7.1 to 7.3 quiz review on everything we've done on sequences and series so far. Hopefully there are not too many questions on monthly repayment things. Thank you so much, guys. Take care. I'm going to see you in the next one.